microcosm.
Look up at the night sky. Go ahead, I'll wait. What do you see? Stars, right? Thousands of them, scattered across the darkness like diamonds on black velvet. But here's what will blow your mind. What you're actually looking at is mostly nothing. Empty space, the void. And that void is not just empty, it's cold. Incomprehensibly, terrifyingly, beautifully cold. Let me put this in perspective for you. When you look at the space between stars, you're looking at something so empty that if you took all the matter in the observable universe and spread it evenly across space, you'd have roughly 1 hydrogen atom per cubic meter. 1 atom, in a space the size of a washing machine. That's how empty the universe really is. We live on a tiny rock orbiting an average star in a galaxy of hundreds of billions of stars, and even here, in this relatively crowded neighborhood, the nearest star to us is so far away that light, moving at 186,000 miles per second, takes more than 4 years to reach us. 4 years at the speed of light just to reach our closest neighbor. Think about that. But distance isn't the only thing that makes space empty. There's also the cold. Space is cold in a way that defies human comprehension. The average temperature of the universe is 2.7 Kelvin. That's minus 270 degrees Celsius, or minus 454 degrees Fahrenheit. We're talking about a temperature so low that it's only 2.7 degrees above the coldest possible temperature in the universe. Absolute zero. At absolute zero, atoms would theoretically stop moving entirely. The universe isn't quite there, but it's close. Uncomfortably close. Now you might be thinking, wait, doesn't the sun heat things up in space? And you'd be right to ask. But here's the thing. The sun heats objects through radiation, not through heating the space itself. Space is a near-perfect vacuum, and heat needs matter to transfer through. When you're standing in sunlight on Earth, you feel warm because the sun's radiation heats your skin, and the warm air around you traps that heat. In space, there's no air, no atmosphere, no matter to hold that heat. Stand in direct sunlight in space, and yes, the side of you facing the sun will heat up dramatically. But turn your back to it and you'll freeze. The void doesn't care about your comfort. Let's talk about what empty really means in space. When I say space is a vacuum, I'm talking about something so devoid of matter that it makes the best laboratory vacuums we can create on Earth look crowded by comparison. In the emptiest regions of intergalactic space, there might be just a handful of atoms per cubic meter. Compare that to the air you're breathing right now, which contains roughly 25 quintillion molecules per cubic meter. That's a 2 followed by 19 zeros. The difference between the air around you and the emptiness of space is so vast that your brain struggles to process it. But here's where it gets even more interesting. Space isn't uniformly empty. It's lumpy. Think of the universe as a cosmic web, with filaments of galaxies and clusters stretching across billions of light years, connected by threads of matter, with enormous voids between them. These voids, these cosmic deserts, are the emptiest places in the universe. Some of them are hundreds of millions of light years across. Imagine a bubble of nearly pure nothingness so large that light itself takes hundreds of millions of years to cross it. These supervoids are the true emptinesses of the universe, places where galaxies are so rare that if you were somehow transported there, you might not see a single galaxy in any direction with the naked eye. You'd be surrounded by darkness so complete, so absolute, that it would make the darkest cave on Earth look like Times Square at midnight. Now, I know what you're thinking. This all sounds pretty depressing, and maybe it is in a way. The universe is indifferent to us. It doesn't care whether we live or die, whether our species survives or perishes. The cold void will outlast us by trillions upon trillions of years. But there's another way to look at it. The fact that we exist at all, that we're here to contemplate this emptiness, is itself extraordinary. We are the universe becoming aware of itself. We are matter that has somehow organized itself into a form complex enough to ask questions about its own existence. That's not nothing. That's everything. Let's dig deeper into the temperature of space. That 2.7 Kelvin I mentioned is not arbitrary. It's the cosmic microwave background radiation, the afterglow of the Big Bang itself. About 380,000 years after the universe began, it had cooled enough for atoms to form and for light to travel freely through space for the first time. That light has been traveling through the expanding universe ever since, cooling as space itself stretches. Until now, it's a faint microwave hiss that permeates everything. It's the oldest light in the universe, a fossil from when the cosmos was just a baby. And it's everywhere. You can't escape it. Point a sensitive enough antenna anywhere in the sky, and you'll pick it up. It's the background temperature of reality itself. But even at 2.7 Kelvin, space isn't the coldest place in the universe. There are places colder than the cosmic background radiation. The Boomerang Nebula, a cloud of gas and dust about 5,000 light-years from Earth, holds the record for the coldest natural place we've ever found. 1 Kelvin, just 1 degree above absolute zero. How is that possible? The nebula is expanding so rapidly that its gas cools as it spreads out, dropping below the temperature of the cosmic microwave background. It's nature's own refrigerator, and it's colder than the space around it. We've also created even colder temperatures in laboratories here on Earth, reaching billionths of a degree above absolute zero. But out there, in the natural universe, the Boomerang Nebula reigns as the coldest place we know. Speaking of cold, let's talk about what happens to matter in these frigid conditions. At the temperatures we're discussing, things behave in ways that seem alien to our everyday experience. Gases condense into liquids, liquids freeze into solids. Chemical reactions slow to a crawl or stop entirely. Even light itself can be affected. At extremely low temperatures, matter can enter quantum states that don't exist at higher temperatures. Atoms can lose their individual identities and merge into a single quantum entity called a Bose-Einstein condensate. Time itself, in a sense, slows down at the atomic level. But the cold is just one aspect of space's emptiness. Let's talk about the vacuum itself, the lack of matter. On Earth, we're used to being surrounded by air. It presses on us from all sides with a force of about 14.7 pounds per square inch at sea level. We don't notice it because we're evolved for it, but it's there, constant and reassuring. Remove that air, create a vacuum, and strange things happen. Water boils at room temperature. Blood tries to vaporize. Your lungs would collapse if you tried to hold your breath. But space? Space doesn't just lack air. It lacks almost everything. The pressure in space is so close to zero that it's essentially unmeasurable. In the emptiest regions of intergalactic space, the pressure is about 10 to the minus 17 pascals. To put that in perspective, that's 10 quadrillionths of the atmospheric pressure on Earth. It's so low that particles of matter are separated by distances that would take hours to cross even at the speed of light. In such a vacuum, there are no collisions between particles. No friction. No sound, because sound needs matter to propagate through. Out there, in the deepest voids, you could scream as loud as you wanted and no one would hear you. Not because they're too far away, although they are, but because there's literally nothing to carry the sound. This emptiness has profound implications for how the universe works. Without matter to slow things down, light travels through space at its maximum speed, unchanging and eternal. Photons that left distant galaxies billions of years ago reach us today having traveled through the void without losing a single bit of information, aside from the redshift caused by the expansion of space itself. That's how we can look back in time. When we look at distant galaxies, we're seeing them as they were billions of years ago because the light has taken that long to reach us through the empty void. But space, as empty as it is, isn't truly nothing. Quantum mechanics tells us that even in the most perfect vacuum, virtual particles constantly pop into and out of existence. They exist for tiny fractions of a second, borrowing energy from the vacuum itself before annihilating and returning that energy. This quantum foam, this bubbling sea of virtual particles, means that true nothingness doesn't exist. Even the void is alive with activity at the quantum level. It's a strange and wonderful paradox. The emptiest places in the universe are actually seething with energy and particles. They just don't last long enough for us to directly observe them. This brings us to one of the greatest mysteries in modern physics: dark energy. The universe isn't just big and empty, it's getting bigger. Space itself is expanding, and not only that, the expansion is accelerating. Galaxies are rushing away from each other faster and faster. The force driving this acceleration is called dark energy, and it makes up about 68% of all the energy in the universe. But here's the kicker: we don't know what it is. We can measure its effects, we can calculate how much of it there must be, but we have no idea what it actually is. It's called dark not because it blocks light, but because we're in the dark about its nature. It's the ultimate invisible hand, pushing the universe apart from within the void itself. And dark energy isn't alone in its mystery. About 27% of the universe is made up of dark matter, invisible matter that doesn't emit, absorb, or reflect light. We know it's there because we can see its gravitational effects on visible matter. Galaxies rotate too fast for the amount of visible matter they contain. They should fly apart. But they don't, because dark matter provides the extra gravity to hold them together. We can map dark matter's distribution by observing how it bends light from distant galaxies, a phenomenon called gravitational lensing. But despite decades of searching, we still haven't directly detected a dark matter particle. It's another ghost in the cosmic machine, invisible and elusive, yet absolutely crucial to the structure of the universe. When you add it all up, the stuff we can see, stars, planets, gas clouds, black holes, all the normal matter made of atoms, makes up less than 5% of the universe. Less than 5%. Everything you've ever seen, touched, or experienced, everything humanity has ever known, is a tiny fraction of what's actually out there. The universe is dominated by things we can't see, held together by forces we don't understand, expanding in ways that defy our intuition. The void is stranger and more complex than we ever imagined. Let's zoom out even further and think about the large-scale structure of the universe. I mentioned earlier that the universe is lumpy, with galaxies clustered along filaments like beads on a string. But the scale of this structure is almost impossible to grasp. The Laniakea supercluster, which contains our Milky Way galaxy along with about 100,000 other galaxies, is about 520 million light-years across. That's the distance light travels in 520 million years. And Laniakea is just one of millions of superclusters in the observable universe. Between these superclusters are the voids I mentioned, enormous bubbles of near emptiness that dwarf even the largest structures. The largest known void is the Eridanus supervoid, a cold spot in the cosmic microwave background that's about 1.8 billion light-years across. Billion, with AB. If you were in the center of this void, the nearest galaxy might be hundreds of millions of light-years away. You'd be alone in a way that's hard to conceptualize. The night sky would be almost completely dark, save for perhaps a handful of faint smudges. You'd be floating in an ocean of nothingness so vast that the human mind struggles to contain it. But even these unimaginable distances pale in comparison to the size of the observable universe itself. The edge of the observable universe is about 46.5 billion light-years away in all directions. Wait, you might say, didn't you tell me the universe is only about 13.8 billion years old? How can we see things that are 46.5 billion light-years away? The answer is expansion. Space itself has been expanding since the Big Bang, carrying distant galaxies away from us faster than light can travel. The light we're seeing now from the most distant galaxies left them when they were much closer, but by the time that light reaches us, those galaxies have moved much farther away due to the expansion of space. It's like trying to walk forward on a treadmill that's moving backward faster than you can walk. And that's just the observable universe. The actual universe is almost certainly much, much larger, possibly infinite. Beyond the edge of what we can see, there are more galaxies, more voids, more of everything, stretching out perhaps forever. We'll never see them because their light hasn't had time to reach us yet, and thanks to the accelerating expansion of space, the light from the most distant regions never will reach us. There are galaxies out there whose light is moving toward us, but space is expanding between us and them faster than the light can close the gap. We exist in a bubble of observability surrounded by an unknowable vastness. Now let's think about the future. The universe is 13.8 billion years old, but it's going to last a lot longer than that. A lot longer. Current models suggest that the universe will continue to expand forever, driven by dark energy. Over time, stars will burn out and die. New stars will form from the remaining gas and dust, but eventually, that too will run out. In about 100 trillion years, the last star will flicker and fade. The universe will enter what's called the degenerate era, dominated by cold stellar remnants, white dwarfs, neutron stars, and black holes. No more stars, no more light, just darkness. But it doesn't end there. Over unimaginably long timescales, even these remnants will decay or be swallowed by black holes. And black holes themselves aren't eternal. Through a process called Hawking radiation, black holes slowly evaporate, losing mass over time. The largest black holes, the supermassive monsters at the centers of galaxies, will take 10 to the power of 100 years to evaporate. That's a googol years, a 1 followed by 100 zeros. The current age of the universe is about 10 to the power of 10 years. We're not even close to 0.1% of the way through the black hole era. And after the black holes evaporate, the universe enters the dark era, a time when all that remains are photons, neutrinos, and other particles scattered across an ever-expanding void. The temperature of the universe will approach absolute zero, not because it's actively cooling, but because the expansion of space dilutes what little energy remains. Eventually, after timescales so long that they make the lifetime of black holes look like the blink of an eye, even protons might decay. Matter itself could break down. The universe would become a cold, dark, empty expanse, devoid of structure, devoid of change, devoid of anything we would recognize as existence. This is the heat death of the universe, the final state toward which everything is moving. It's a bleak vision, isn't it? Everything we are, everything we've built, everything we care about will eventually dissolve into the void. The stars will die. The galaxies will drift apart. Even matter itself will decay. In the end, there will be nothing but cold, empty space, stretching on forever. If you're feeling existential dread right now, I don't blame you. The universe's ultimate fate is one of the most profoundly melancholic things we've discovered. But here's the thing. That end is so far in the future that it's essentially meaningless to us. The universe as we know it still has trillions of years ahead of it before the last star dies. Humanity has existed for maybe 300,000 years. Civilization as we know it is only about 10,000 years old. We have time. More time than we can possibly use. The universe may be cold and empty, but right now, right here, it's also full of wonder and possibility. Think about it. We live in a time when stars are being born, when galaxies are colliding and merging, when planets are forming around distant suns. We live in the stelliferous era, the age of stars, when the universe is at its most interesting and dynamic. We exist during the brief cosmic moment when intelligence is possible, when matter has organized itself into forms complex enough to wonder about the void. That's not an accident. That's not coincidence. It's the universe looking at itself through our eyes. And we're making good use of that opportunity. Every day we learn more about the cosmos. We've sent probes to the edge of our solar system and beyond. Voyager 1 and 2 are out there right now, traveling through interstellar space, carrying messages from Earth into the void. We've landed robots on Mars, sent orbiters to Jupiter and Saturn, and even crashed a probe into a comet. We've built telescopes so powerful they can see galaxies billions of light years away, allowing us to peer back in time to when the universe was young. The James Webb Space Telescope is showing us the first galaxies that formed after the Big Bang, giving us glimpses of the cosmic dawn. We've also learned that the universe is far stranger than we ever imagined. Black holes aren't just cosmic vacuum cleaners. They're laboratories for extreme physics, places where the laws of nature are pushed to their limits. Neutron stars, the collapsed cores of dead stars, are so dense that a teaspoon of their material would weigh as much as a mountain. They spin hundreds of times per second and have magnetic fields 1,000,000,000,000 times stronger than Earth's. Some of them, called pulsars, emit beams of radiation that sweep across space like cosmic lighthouses, sending precise pulses of radio waves that we can detect from Earth. And then there are the truly bizarre objects. Magnetars, neutron stars with magnetic fields so strong they could strip the atoms from your body from thousands of miles away. Quasars, supermassive black holes at the centers of distant galaxies that shine brighter than trillions of stars. Gamma ray bursts, the most energetic explosions in the universe, releasing more energy in a few seconds than the sun will emit in its entire lifetime. The universe is full of wonders, even in its emptiness. But let's get back to that emptiness, because it's truly the defining characteristic of the cosmos. To really understand how empty space is, let's do a thought experiment. Imagine you could somehow shrink the sun down to the size of a basketball. On that scale, Earth would be about the size of a peppercorn, orbiting about 26 feet away. Jupiter would be about the size of a cherry, orbiting about 140 feet away. Neptune, the farthest planet in our solar system, would be a small pebble about 800 feet away. Already, at this scale, our solar system is surprisingly empty. But the nearest star, Proxima Centauri, would be another basketball 1,300 miles away. That's the distance from New York to Miami, and that's the nearest one. Scale that up to galactic distances, and the emptiness becomes even more apparent. The Milky Way galaxy contains somewhere between 100 and 400 billion stars, but the distances between them are so vast that if you were traveling at the speed of light, it would take you years or decades to reach the nearest ones. And between galaxies, the void is even more extreme. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. That's the distance light travels in 2.5 million years. And Andromeda is close, cosmically speaking. Most galaxies are billions of light-years away, separated by voids so large they make intergalactic space look crowded. This emptiness isn't just a curiosity. It has profound implications for the fate of the universe and for the possibility of life elsewhere. The vastness of space means that even if life is common in the universe, civilizations would be separated by distances so great that communication, let alone travel, would be incredibly difficult. If the nearest intelligent civilization is, say, 1,000 light-years away, then a message sent to them would take 1,000 years to arrive, and their response would take another 1,000 years to get back to us. That's a 2,000-year round-trip conversation. By the time we got their response, our civilization might be unrecognizable, or might not even exist anymore, and that assumes we could somehow send a message that would survive the journey through the void. Space is not a friendly place for delicate electronic signals. Cosmic rays, high-energy particles from supernovae and other violent events, constantly bombard everything in space. They can damage electronics, degrade materials, and even alter DNA. A spacecraft traveling through interstellar space would be constantly battered by this radiation. Shielding helps, but it adds weight, and weight is the enemy of space travel. The void is not just empty, it's actively hostile to complex structures. Yet despite all this, life managed to arise here on Earth. Against all odds, in a universe that's mostly empty and cold, a tiny fraction of the matter in one small corner of space organized itself into living, thinking beings. We are, in Carl Sagan's famous phrase, star stuff contemplating stars. The atoms in your body were forged in the nuclear furnaces of stars that lived and died billions of years ago. The carbon in your cells, the oxygen you breathe, the calcium in your bones. All of it was created in stellar cores and scattered across space when those stars exploded as supernovae. You are literally made of stardust, a collection of atoms that has somehow become aware of its own existence. This is perhaps the most amazing thing about the universe's emptiness. Despite being dominated by void and cold and darkness, the universe is capable of producing islands of complexity and warmth and light. Stars are born in the collapse of gas clouds, shining bright against the darkness. Planets form from the debris left over, some of them rocky and warm and wet, perfect for the emergence of life. And life, once it starts, is incredibly tenacious. It finds ways to survive in the most extreme environments, from the frozen wastes of Antarctica to the superheated waters near deep-sea volcanic vents. If life can thrive in such extremes here on Earth, who's to say it couldn't arise on some distant exoplanet, orbiting some distant star, in some distant galaxy? We've already found thousands of exoplanets, worlds orbiting other stars. Some of them are hot Jupiters, massive gas giants that orbit closer to their stars than Mercury does to our Sun. Others are super-Earths, rocky worlds larger than Earth but smaller than Neptune. And some, just a handful so far, are in the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. Water is essential for life as we know it, so these worlds are our best bet for finding extraterrestrial life. But even in the habitable zone, conditions might not be right. A planet needs the right atmosphere, the right temperature, the right chemistry. It needs to be protected from harmful radiation and asteroid impacts. It needs to be stable over billions of years, long enough for complex life to evolve. Earth had all of those things. We had liquid water, a stable climate, a protective magnetic field, and a large moon to stabilize our rotation. We had plate tectonics to recycle nutrients and regulate the atmosphere. We had just the right amount of asteroid impacts, enough to deliver water and organic compounds, but not so many that they sterilized the planet. In short, we got lucky. Really, really lucky. The question is, how lucky? Is life rare in the universe, or is it common? Are we alone, or are there others out there, looking up at their night skies and wondering the same thing? This is the Fermi paradox, named after physicist Enrico Fermi. If the universe is so big and so old, and if life is common, where is everybody? Why haven't we detected any signals from alien civilizations? Why haven't they visited us? There are many possible answers. Maybe life is rare. Maybe intelligence is rare. Maybe technological civilizations destroy themselves before they can spread to the stars. Maybe the distances are just too great and the void too vast for anyone to cross it. Maybe we're looking in the wrong places or listening on the wrong frequencies. Maybe alien civilizations are out there, but they're using technologies we can't even imagine, let alone detect. Or maybe we're alone. Maybe Earth is the only place in the entire observable universe where life exists. It's a lonely thought, but it's also empowering. If we're the only ones, then we're precious beyond measure. We're the universe's only way of knowing itself, at least in this corner of space. That gives us a responsibility to survive, to spread, to keep the flame of consciousness burning against the cold darkness. But I don't think we're alone. The universe is too big, too old, too full of possibilities for Earth to be the only world with life. Somewhere out there, in the vast emptiness, there must be others. Maybe they're microbes living in the subsurface oceans of distant moons. Maybe they're intelligent beings building civilizations on worlds we'll never see. Maybe some of them have already discovered us, observing us from afar, waiting to see if we'll survive our own technological adolescence. We don't know, but the universe is patient. It has time, and so do we if we're smart about it. Let's talk about the nature of the void itself. What is nothing, really? Philosophers have debated this for millennia, but physics gives us some concrete answers. In quantum field theory, empty space is described as a vacuum state, the lowest energy state of a system. But even in this lowest energy state, the vacuum is not truly empty. Quantum fields permeate all of space, and these fields are constantly fluctuating, creating and destroying virtual particles. These fluctuations are real. They have measurable effects. For instance, the Casimir effect, where two uncharged metal plates placed very close together in a vacuum will be pushed together by the quantum fluctuations of the vacuum between them. It's a tiny effect, but it's their proof that the vacuum is not nothing. These quantum fluctuations might even be responsible for the existence of the universe itself. In inflationary cosmology, the leading theory of the early universe, a quantum fluctuation in a primordial field caused space to expand exponentially, growing from smaller than an atom to larger than a galaxy in a fraction of a second. This inflation smoothed out the universe and set the stage for the formation of structures like galaxies and stars. In other words, the entire universe might have started as a quantum hiccup in the void. Something from nothing, or at least something from almost nothing. This brings us to one of the deepest questions in cosmology. Why is there something rather than nothing? Why does the universe exist at all? We don't have a definitive answer, but there are some intriguing possibilities. Some physicists suggest that the laws of physics themselves might make nothing unstable, that a true vacuum would spontaneously give rise to something. Others propose that our universe is just one of many in a vast multiverse, each with different laws of physics, and we happen to exist in one that allows for complexity and life. Still, others argue that the question itself might be meaningless, that the concept of nothing is incoherent and that something must always have existed. Whatever the answer, the fact remains that we live in a universe that is mostly empty, mostly cold, mostly dark. And yet, here we are. Against all odds, in defiance of entropy and the second law of thermodynamics, we exist. We are pockets of order in a universe trending toward disorder, islands of warmth in an ocean of cold, sparks of light in an expanding darkness. We are the universe's rebellion against its own nature. And we're not just passive observers. We're active participants in the cosmic story. Every time we launch a spacecraft, we're sending a message into the void. We were here. Every time we build a telescope and peer deeper into space, we're extending our reach, expanding the bubble of the known. Every time we ask a question about the universe, we're honoring the strange fact that matter can think, that atoms can wonder about atoms. That's a miracle as profound as any in religion, and it's happening right now, all around us, all the time. Consider the cosmic calendar, a way of visualizing the history of the universe by compressing all 13.8 billion years into a single calendar year. On this scale, the Big Bang happens at midnight on January 1st. The Milky Way forms in March. Our solar system and Earth form in early September. Life appears on Earth in late September. The first multicellular organisms don't show up until November. Dinosaurs rule the Earth for a few days in mid-December and go extinct on the evening of December 26th. Modern humans appear at 11:50 p.m. on December 31st. All of recorded history, every empire that has risen and fallen, every war fought, every symphony composed, every word written, happens in the last 14 seconds of the year. That's how brief our existence is on cosmic timescales. We're latecomers to the universe, Johnny-come-latelys, showing up in the last fraction of a percent of cosmic history. And yet, in that brief moment, we've accomplished remarkable things. We've decoded the laws of nature, mapped the genome, split the atom, walked on the moon, and peered back to the beginning of time itself. We've learned that we're made of star stuff, that we live in an expanding universe, that reality is stranger and more wonderful than our ancestors ever imagined. But our time is limited, not just individually, though that's true too, but as a species. If we don't leave Earth, if we don't spread to other worlds, then eventually we'll go extinct. Maybe it'll be an asteroid impact, maybe a supervolcano, maybe climate change, maybe something we do to ourselves. The universe is full of extinction events, and Earth has already had several. The dinosaurs found that out the hard way 66 million years ago. We're smarter than dinosaurs. We can see these threats coming and potentially do something about them. But only if we act. This is why space exploration matters. Not just because it's cool, though it definitely is, but because it's essential for the long-term survival of our species. We need to become a multiplanetary civilization. We need to establish colonies on Mars, on the moons of Jupiter and Saturn. We need to build habitats in space, rotating cylinders where people can live and work and raise families. We need to send ships to other star systems to find new worlds and new homes for humanity. It's not going to be easy. Space is hard. The void is unforgiving, but it's possible and it's necessary. And it's not just about survival. It's about growth, about fulfilling our potential as a species. We're explorers by nature. We've always pushed beyond the horizon, always wondered what's on the other side of the mountain, across the ocean, beyond the atmosphere. Space is the ultimate frontier, the final unexplored territory. Out there, in the void, there are discoveries waiting that will transform our understanding of reality. There are resources to be tapped, energy to be harvested, worlds to be settled. The universe is full of possibilities, and we're only just beginning to reach for them. Let me paint you a picture of the future. 1,000 years from now, humanity has spread throughout the solar system. There are cities on Mars, domed habitats on the Moon, floating colonies in the clouds of Venus. Miners extract resources from asteroids, hauling back water ice and precious metals to fuel the expansion. Scientists work in laboratories on Europa and Enceladus, studying the subsurface oceans of these moons, searching for signs of life. Engineers build massive solar arrays in orbit around the sun, capturing its energy and beaming it to wherever it's needed. And beyond the solar system, the first interstellar missions have been launched, robotic probes traveling at a significant fraction of the speed of light, carrying seeds of life and human knowledge to the stars. Maybe some of them find habitable worlds and report back, sending data across the light years, telling us what they've found. Maybe some of them even carry frozen embryos or digital blueprints for humans, ready to be realized when they reach their destinations. Sounds like science fiction, but the physics is sound. We could do this. We just need the will and the resources. 10,000 years from now, humanity might be scattered across dozens or hundreds of star systems, each one developing its own culture, its own way of life, adapted to its unique environment. We'll be diversifying, spreading our bets across the cosmic table, ensuring that no single event can wipe us out. And we'll be learning. Each new world will teach us something about the nature of life, about the possibilities of existence. We'll encounter conditions and environments we never imagined, and we'll adapt to them, because that's what life does. Finds a way. 1,000,000 years from now, I can't even imagine. Maybe we'll have spread across the galaxy, a civilization of trillions living on millions of worlds. Maybe we'll have encountered other intelligent species, learning from them and teaching them in turn. Maybe we'll have transformed ourselves, augmenting our biology with technology, extending our lifespans, enhancing our minds. Maybe we'll have solved the fundamental mysteries of physics, learning to harness dark energy, to create wormholes, to manipulate space and time itself. Or maybe we'll be gone, extinct, a brief flash of consciousness in the long dark night of the cosmos. We don't know. The future is not written, but the potential is there. And even if we fail, even if humanity goes extinct and the Earth becomes a lifeless rock circling a dying star, the universe will continue. New stars will be born. New planets will form. Maybe somewhere, somehow, life will arise again. Maybe it will learn to think, to wonder, to explore. Maybe it will look up at the stars and ask the same questions we're asking now. And maybe it will do better than we did. Maybe it will spread and thrive and endure, keeping the flame of consciousness alive for eons to come. Because that's the thing about the universe. It's patient. It has time. More time than we can possibly comprehend. The stars will shine for trillions of years. The black holes will evaporate over googolls of years. The universe will expand forever, becoming colder and emptier and darker, but it will still be here. And as long as there's time, there's possibility. There's hope. So yes, the universe is cold. Yes, it's empty. Yes, it's vast beyond comprehension. And yes, it will eventually become a frozen, dark, lifeless expanse. But right now, right here in this tiny corner of space and time, there is warmth. There is life. There is thought. We exist. That matters. That means something. We are the universe's way of fighting back against the cold, against the emptiness, against the void. We are its way of saying, not yet, not today. Every breath you take is an act of defiance against entropy. Every thought you think is a rebellion against the heat death of the universe. Every connection you make, every kindness you show, every work of art you create, every question you ask, every answer you seek. All of it is part of the grand cosmic story, a story that began 13.8 billion years ago with a burst of inconceivable energy and that continues today in your mind, in your heart, in your very existence. The void is vast, but we are here. The universe is cold, but we are warm. The darkness is deep, but we are light. We are star stuff that has learned to wonder about stars. We are atoms that have learned to ask about atoms. We are the universe waking up, looking around, and trying to figure out what the hell is going on. And that's beautiful. That's profound. That's worth preserving, worth protecting, worth spreading to the stars. So when you look up at the night sky, don't just see the emptiness between the stars. See the possibilities. See the potential. See the challenge and the opportunity. We live in a universe that is mostly void, but that void is filled with possibility. It's waiting for us to explore it, to understand it, to fill it with life and meaning and purpose. The universe may be indifferent to us, but we're not indifferent to it. We care. We wonder. We dream. And that makes all the difference. The cold emptiness of the universe is not a prison. It's an invitation to explore, to discover, to grow, to become something more than we are. Out there, in the void, there are worlds waiting to be discovered, mysteries waiting to be solved, adventures waiting to be lived. The universe is vast and ancient and strange, full of wonders beyond our imagining. And we're part of it. We belong here, in this cosmic dance of matter and energy, of space and time. We're not separate from the universe. We're expressions of it, just as much as stars and galaxies and black holes. So yes, space is cold. Space is empty. Space is dark and vast and mostly nothing. But it's also the stage on which the greatest drama in existence is playing out. The story of matter organizing itself into increasingly complex forms, of atoms becoming molecules, becoming cells, becoming organisms, becoming consciousness. It's the story of the universe becoming aware of itself, of nothingness giving rise to everything, of the cold void producing islands of warmth and light and life. And we're the protagonists of that story, at least for now, at least in this small corner of space. We're the ones asking the questions, seeking the answers, pushing back the boundaries of the unknown. We're the ones who looked up at the stars and decided to visit them. We're the ones who peered into the void and saw not emptiness, but opportunity. We're the ones who refused to accept that the cold and the darkness will have the last word. Because here's the ultimate truth, the final revelation. The universe may be vast and cold and empty, but it's also ours. We're part of it. We emerged from it. We're made of it. Every atom in your body, every thought in your mind, every feeling in your heart. All of it is the universe expressing itself, experiencing itself, understanding itself. You are the universe looking back at itself through human eyes. You are a way for the cosmos to know itself. And that is not a small thing. That is everything. So the next time someone tells you that the universe is cold and empty and meaningless, tell them they're half right. Yes, it's cold. Yes, it's empty. But meaningless? No, we're the meaning. We're the light in the darkness, the warmth in the cold, the something in the nothing. We're the universe's answer to its own emptiness. And as long as we're here, as long as we continue to look up at the stars and wonder, as long as we continue to ask questions and seek answers and push the boundaries of the possible, the universe is anything but meaningless. The void may be infinite, but so is our capacity for wonder. The darkness may be deep, but our light can shine into it. The cold may be absolute, but our passion for discovery burns hot enough to warm us against it. We are children of the cosmos, and we have inherited a universe that is ours to explore, ours to understand, ours to fill with meaning and purpose and life. This is our moment. This is our time. We live in an age of discovery, in an era when we're taking our first tentative steps beyond our home world, when we're learning to read the cosmic story written in light and gravity and radiation. We're mapping the structure of the universe, measuring the expansion of space, detecting gravitational waves from colliding black holes billions of light years away. We're finding planets around other stars, searching for signs of life beyond Earth, preparing to send humans back to the moon and onward to Mars. We're living through the beginning of humanity's transformation from a single-planet species to a spacefaring civilization. And future generations will look back on this time with wonder and perhaps envy. They'll read about the first moon landings, the first Mars colonies, the first discoveries of life on other worlds, and they'll wish they could have been there to see it. They'll marvel at our audacity, our courage, our willingness to venture into the unknown despite the risks, despite the challenges, despite the cold emptiness waiting for us in the void. They'll understand that we were the generation that opened the door to the cosmos, that took humanity's first real steps toward its ultimate destiny among the stars. So don't fear the void. Embrace it. It's not an enemy. It's a canvas, blank and waiting for us to paint on it. It's a question waiting for our answer. It's a challenge waiting for us to accept. The cold emptiness of the universe is not the end of the story. It's the beginning. It's where everything starts, and it's where everything is possible. The universe is 13.8 billion years old. It's filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. It's expanding, accelerating, rushing toward a future of ever-increasing emptiness and cold. But right now, in this moment, on this tiny planet orbiting this average star in this unremarkable galaxy, there are billions of human beings living their lives, dreaming their dreams, reaching for the stars. And that's not nothing. That's everything. We stand at the edge of the infinite, looking out into the darkness, and we're not afraid. We're curious. We're excited. We're ready to explore, to discover, to learn. The void may be cold, but we have each other. The universe may be empty, but we fill it with meaning. The darkness may be vast, but we are the light. This is the cold emptiness of the universe. A blank page waiting for us to write on it. A dark sky waiting for us to fill it with light. A silent void waiting for us to fill it with the noise and bustle and beautiful chaos of life. The universe has given us an incredible gift. Existence itself, consciousness, the ability to wonder and to understand. And our gift back to the universe is to refuse to let that light go out, to keep the flame of awareness burning, to spread life and consciousness and meaning into every corner of the cosmos that we can reach. So when you look up at the stars tonight, remember, you're not just seeing distant suns. You're seeing possibilities. You're seeing potential. You're seeing the future of humanity written in light across the sky. The void is calling to us, inviting us to explore it, to understand it, to make it ours. And we will answer that call. We must, because we are explorers. We are discoverers. We are humans, and the universe is our home. Now let's talk about what it would actually be like to travel through this void. Imagine you're on a spacecraft heading away from Earth, away from the sun, out into interstellar space. At first, you'd still see the sun behind you, bright and warm. But as you traveled farther, it would shrink, becoming just another star in the sky. The planets would disappear, too faint to see with the naked eye. Eventually, even the sun would be just a bright point of light, indistinguishable from the other stars. And you'd be alone, truly alone, in a way that's hard to comprehend. The silence would be absolute. In space, there's no air to carry sound, so you wouldn't hear anything except the hum of your spacecraft systems and your own heartbeat. Outside, there would be perfect silence, a quietness so complete that it would be almost physical, pressing in on you from all sides. And the darkness. Oh, the darkness. Without the sun's light, space is dark in a way that nothing on Earth can match. You'd see the stars, of course, but they're so far away that their light barely registers. Most of space is just empty blackness, a void so deep and so dark that your eyes would strain to find anything to focus on. And the temperature. Your spacecraft would need to be insulated because outside, in the void, the temperature is hovering just above absolute zero. Any part of your ship exposed to space would radiate away its heat until it reached equilibrium with the cosmic microwave background. That's 2.7 Kelvin, remember, cold enough to freeze anything solid, cold enough to make molecules stop moving, cold enough to kill you in minutes if your life support failed. The void doesn't care about your comfort. It doesn't care about you at all. But there's a strange beauty to it too. The stars would shine with a clarity impossible to achieve on Earth, unfiltered by atmosphere, undiminished by air pollution or light pollution. You'd see colors in the stars, subtle variations from white to blue to red to yellow, each one telling a story about the star's temperature and composition. You'd see the band of the Milky Way stretching across the sky, a river of light made up of hundreds of billions of stars, all too far away to see individually, but collectively creating a glowing path across the darkness. And if you waited long enough, if you were patient, you might see a galaxy, a faint smudge of light billions of light years away, its light having traveled across the universe for eons just to reach your eyes at that moment. This is what the void is really like. Empty, yes, but also full of wonder. Cold, yes, but also beautiful. Dark, yes, but also illuminated by the light of a billion stars. It's a place of extremes, of contradictions, of profound loneliness and equally profound awe. It's a place that will kill you without hesitation, but also a place that will show you wonders beyond imagining. The void is not your friend, but it's not your enemy either. It just is indifferent and eternal, waiting for you to explore it. Let's think about the scale of interstellar travel. The fastest spacecraft we've ever built, the Parker Solar Probe, travels at about 430,000 miles per hour when it's at its fastest, diving close to the sun. That sounds incredibly fast, and it is by human standards. But at that speed, it would still take about 6,800 years to reach Proxima Centauri, the nearest star to our sun, 6,800 years. That's longer than recorded human history. The ancient Egyptians were building pyramids 6,800 years ago, and we're still here, still human, still basically the same species. But would we be in another 6,800 years? Would our civilization even exist? It's hard to say, and that's just to reach the nearest star. To cross the galaxy, to travel from one side of the Milky Way to the other, would take millions of years at current speeds. To reach another galaxy, billions of years. The distances are so vast that they make a mockery of our ambitions. The void is not just empty. It's also immense, so incomprehensibly large that it defeats our attempts to cross it with brute force. But maybe we don't need to cross it. Maybe the solution isn't faster ships, but longer lives. If we could extend human lifespan to thousands or millions of years, suddenly interstellar travel becomes feasible. You could spend centuries traveling between stars, exploring, learning, experiencing. Time would become meaningless in a way. What's a few hundred years when you have millions ahead of you? Of course, this raises other questions. Would you still be human after living for 1,000,000 years? Would you still remember who you were when you started? Would you even want to? The void changes everything, including our understanding of what it means to be alive, to be conscious, to be human. Or maybe the solution is to not send humans at all, at least not biological humans. Send machines, artificial intelligences that don't need air or food or warmth, that can survive the cold and the radiation and the loneliness of the void. They could travel between the stars, exploring, gathering data, sending it back to us. Or they could carry digital copies of human minds, uploaded consciousnesses that exist as software rather than wetware. You could live forever in a digital realm, experiencing virtual worlds while your ship's body travels through the physical void. When you arrive at your destination, you could download yourself into a new body, whether biological or mechanical, and continue your existence on a new world. The void might be impassable for flesh and blood, but for information, for data, it's just another medium to be crossed. These aren't just science fiction fantasies. These are real possibilities that scientists and engineers are seriously considering. We're already working on life extension technologies, on artificial intelligence, on brain-computer interfaces. We're laying the groundwork for a future where humanity might transcend its biological limitations and spread across the cosmos in forms we can barely imagine today. The void is a challenge, but it's not insurmountable. We just need to be creative, to think beyond our current limitations, to embrace the strangeness and the possibility of what we might become. Let's talk about the cosmic voids themselves, those enormous bubbles of near emptiness between the galaxy clusters. These supervoids are some of the largest structures in the universe, hundreds of millions of light years across, containing very few galaxies. The largest one we know of, the Boötes void, is about 330 million light years across and contains only about 60 galaxies, compared to the thousands you'd expect to find in a similar volume of space elsewhere. It's so empty that if the Milky Way were in the center of the Boötes void, we wouldn't have known other galaxies existed until the 1960s, when our telescopes became powerful enough to detect the faint smudges of light at the void's edges. Imagine living in a galaxy within such a void. Your night sky would be almost completely dark, save for the stars of your own galaxy. No spiral nebulae, no fuzzy patches that turn out to be other galaxies when you look through a telescope. Just darkness. You'd have no idea that the universe was full of other galaxies, that you were living in an anomalously empty region of space. Your cosmology, your understanding of the universe would be completely different. You might think your galaxy was all there was, that beyond its edges there was nothing but infinite void. And you'd be partly right. There would be void, vast and empty, stretching for hundreds of millions of light years in all directions. It's only at the edges of that void, impossibly far away, that other galaxies would finally appear. These voids formed in the early universe, when quantum fluctuations in the primordial density field created regions of slightly higher and slightly lower density. The higher density regions gravitationally attracted more matter, growing into the galaxy clusters and filaments we see today. The lower density regions, meanwhile, were emptied as their matter was pulled toward the denser areas. Over billions of years, these regions grew into the supervoids we observe, enormous bubbles where expansion has carried away most of the matter, leaving behind only a sparse scattering of galaxies. And here's something fascinating. These voids are expanding faster than the rest of the universe. Because they contain less matter, they have less gravity to slow down the expansion of space. Dark energy, that mysterious force driving the acceleration of the universe, has a stronger effect in the voids because there's less matter to counteract it. The voids are growing, becoming emptier, pushing the galaxy clusters farther apart. In the far future, as dark energy continues to dominate, the voids will grow even larger, and the clusters will become more isolated. Eventually, billions of years from now, galaxies in different clusters will be so far apart that light from one will never reach the other. The universe will fragment into causally disconnected regions, islands of matter separated by voids so vast that no signal, no light, no information can ever cross them. Each galaxy cluster will be alone, truly alone, in its own bubble of observable space. But that's billions of years away. Right now, the voids are still crossable, at least in principle. Light from galaxies on one side of a void can still reach galaxies on the other side. The universe is still connected, still a single coherent structure. And that's important because it means the universe has a history, a story that can be traced from the Big Bang to the present, a narrative of cosmic evolution that we can reconstruct by observing distant galaxies and the cosmic microwave background. Speaking of which, let's talk more about that cosmic microwave background, that faint glow that fills all of space. It's one of the most important discoveries in cosmology, proof that the universe had a beginning, that it was once hot and dense and has been expanding and cooling ever since. When you tune a radio to a frequency that's not being used by any station, about 1% of the static you hear is actually the cosmic microwave background. You're listening to the echo of the Big Bang itself, a signal that's been traveling through space for 13.8 billion years. This background radiation is remarkably uniform. In every direction you look, it has almost the same temperature, 2.725 Kelvin to be precise. Almost the same, but not quite. There are tiny fluctuations, variations of about 1 part in 100,000, hot spots and cold spots that correspond to regions of slightly higher and slightly lower density in the early universe. These fluctuations are the seeds from which galaxies and galaxy clusters grew. The hot spots were regions where matter was slightly denser, where gravity was slightly stronger, pulling in more matter and eventually forming the structures we see today. Mapping these fluctuations has been one of the great triumphs of modern cosmology. Satellites like COBE, WMAP, and Planck have measured the cosmic microwave background with exquisite precision, creating maps of the early universe that show us what it looked like just 380,000 years after the Big Bang. These maps have told us the age of the universe, the composition of matter and energy, the rate of expansion, and much more. They've confirmed that the universe is flat, that it's made mostly of dark matter and dark energy, that it went through a period of rapid inflation in its earliest moments. The cosmic microwave background is a fossil, a relic from the universe's infancy, and it's taught us more about cosmology than almost any other observation. And it's everywhere. You can't escape it. Go to the emptiest void, the darkest, coldest corner of the universe, and the cosmic microwave background will still be there. A faint reminder that the universe had a beginning, that it's evolving, that it's headed toward a future we can predict but perhaps not fully comprehend. It's the ultimate background noise, the static of existence itself, and it connects us to the very birth of reality. Let's think about what space smells like. You might not think this is an important question, but astronauts who have done spacewalks report that space has a distinct odor. When they come back inside and remove their helmets, they notice a smell clinging to their suits. They describe it variously as metallic, like welding fumes, or sweet, like burnt steak, or acrid, like gunpowder. The smell comes from high-energy particles, cosmic rays, and solar wind that collide with the spacecraft and the spacesuits, creating complex organic molecules and ozone. So space doesn't just look and feel alien. It smells alien too. This might seem like a trivial detail, but it's a reminder that space is not just an abstract concept, not just a mathematical description of emptiness and cold. It's a real place with real physical properties, and when we go there, we experience it with all our senses. The void is not just something we observe from a distance. It's something we can touch, smell, feel. It's something we can explore directly with our own bodies, our own senses, our own presence. And that makes it real in a way that no amount of theory or observation can match. Of course, spending too long in space is bad for you. Astronauts on the International Space Station experience bone density loss, muscle atrophy, vision problems, and increased radiation exposure. Their cardiovascular systems weaken because they don't have to work against gravity. Their immune systems become less effective. Even their telomeres, the protective caps on the ends of chromosomes, behave differently in space. The void is harsh, and it takes a toll on the human body. We're adapted for life on Earth for one gravity, for a protective atmosphere and magnetic field. Space is none of those things. It's hostile to us in fundamental ways. But we're working on solutions. Scientists are studying how to counteract the effects of microgravity through exercise and medication. They're developing better shielding against radiation. They're even experimenting with artificial gravity, spinning spacecraft or habitats to create centrifugal force that mimics the pull of Earth's gravity. We're learning how to survive in the void, how to adapt to it, how to make it our home. It won't be easy and it won't be comfortable, but it's possible. We're stubborn like that. We see a challenge and we rise to meet it. And we'll need to because the void is our future. Earth won't last forever. In about 1 billion years, the sun will have grown hot enough that Earth's oceans will evaporate. The planet will become uninhabitable. In 5 billion years, the sun will expand into a red giant, engulfing Mercury and Venus and possibly Earth as well. Our home world will be destroyed, consumed by the dying star that gave it life. That sounds far away, and it is, but on cosmic timescales, it's just around the corner. If humanity is going to survive long-term, we need to leave Earth. We need to spread to other worlds, other star systems, other galaxies. We need to embrace the void, to make it our domain, to ensure that when Earth dies, we don't die with it. This is not optional. It's not a matter of if, but when. The universe is going to destroy our planet. It's going to destroy our sun. Eventually, it's going to destroy our galaxy. The void is patient, and it's relentless, and it will outlast anything we can build. But that doesn't mean we should give up. It means we should plan ahead. We should start now, building the technologies and the infrastructure we'll need to survive in space, to thrive in the void, to spread across the cosmos. Because if we don't, then everything we are, everything we've built, everything we've learned, will vanish without a trace. And that would be a tragedy of cosmic proportions. Let's talk about the speed of light because it's central to understanding the void. Light travels at 299,792,458 meters per second in a vacuum. That's not just fast. It's the fastest speed possible in the universe, according to Einstein's theory of relativity. Nothing with mass can reach the speed of light, and nothing, not even information, can travel faster than light. This is a fundamental law of physics, and it has profound implications for space travel and communication. At the speed of light, you could travel from Earth to the Moon in about 1.3 seconds. You could reach Mars in about 3 minutes when it's at its closest. You could reach the edge of the solar system in about 5.5 hours. But to reach Proxima Centauri, the nearest star, would take 4.24 years. To cross the Milky Way would take 100,000 years. To reach Andromeda would take 2.5 million years. And that's at the speed of light, which, remember, is impossible for anything with mass to achieve. Any realistic spacecraft would travel much slower, meaning interstellar journeys would take tens of thousands or millions of years. This speed limit creates what's called the light cone, the region of spacetime that can be affected by or can affect a given event. If something happens here and now, its effects can only propagate outward at the speed of light, creating a cone-shaped region in spacetime. Events outside this cone cannot be affected by or affect the original event. This means that for distant parts of the universe, we're causally disconnected. We can observe them, but we can't interact with them in any meaningful way. They're beyond our light cone, forever out of reach. And because the universe is expanding, and the expansion is accelerating, this problem gets worse over time. There are galaxies that we can see now whose light is reaching us, but because space is expanding between us faster than light can travel, we will never be able to send a signal to them. They're beyond what's called the cosmic event horizon, the boundary of the region of space with which we can ever have causal contact. As the universe ages, this horizon will shrink, cutting us off from more and more of the cosmos. Eventually, billions of years from now, we'll only be able to see and interact with galaxies in our local group, the few dozen galaxies bound together by gravity. Everything else will have been carried away by expansion, receding beyond the event horizon, disappearing from view forever. This is one of the strangest and saddest facts about the universe. We live at a privileged time, when the universe is young enough that we can still see most of it, when light from distant galaxies has had time to reach us but hasn't been redshifted into invisibility yet. Future civilizations, if they exist, will look up at the sky and see only their local group, a handful of galaxies surrounded by darkness. They won't know that the universe is expanding. They won't know about the Big Bang. They won't have the cosmic microwave background to study because it will have been redshifted into undetectability. Their cosmology will be limited, their understanding of the universe incomplete, through no fault of their own, but simply because they were born too late. The void will have taken the evidence away from them, We, on the other hand, are lucky. We live when we can still see the universe in all its glory, when we can still trace its history back to the beginning, when we can still observe the cosmic microwave background and the expansion of space and all the other phenomena that tell us about where we came from and where we're going. We have a window into the cosmos that future generations won't have. That's both a privilege and a responsibility. We need to learn as much as we can while we still can, because the universe won't always be so generous with its secrets. Now let's talk about one of the most mind-bending aspects of the void, the nature of space-time itself. Einstein's general relativity tells us that space and time are not separate things but aspects of a single four-dimensional fabric called space-time. Matter and energy curve this fabric, and that curvature is what we experience as gravity. Massive objects like stars and planets create dips in space-time, and other objects roll into those dips, which we perceive as gravitational attraction. But what about the void, the empty space between objects? Is it really empty? According to general relativity, even empty space has properties, can curve, can expand. It can even carry energy in the form of gravitational waves, ripples in space-time caused by accelerating masses. These waves travel at the speed of light, carrying information about violent cosmic events like colliding black holes or exploding stars. We've only recently learned to detect them, but they've been there all along, crisscrossing the universe, stretching and squeezing space itself as they pass. In 2015, for the first time in history, we directly detected gravitational waves. The LIGO observatories, two enormous laser interferometers located in Louisiana and Washington, picked up the signal from two black holes colliding 1.3 billion light-years away. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. The waves traveled across the void for 1.3 billion years, stretching and squeezing space as they went, until finally they reached Earth and caused the mirrors in LIGO to move by less than 1,000th of the diameter of a proton. And we detected it. We measured it. We confirmed that gravitational waves are real, that space-time can ripple like the surface of a pond, that the void itself can carry information about the most violent events in the universe. Since then, we've detected dozens more gravitational wave events. Colliding black holes, colliding neutron stars, events that released unimaginable amounts of energy into the fabric of space itself. Each detection teaches us something new about the nature of space-time, about the behavior of matter under extreme conditions, about the structure and evolution of the universe. Gravitational wave astronomy is a new way of observing the cosmos, complementing traditional light-based astronomy, giving us eyes to see things that are invisible to normal telescopes. The void is not just a passive emptiness. It's an active medium, capable of carrying waves and information, of being shaped and reshaped by the objects within it. And then there's quantum mechanics, which tells us that at the smallest scales, space-time itself might not be smooth and continuous but granular, made up of discrete units smaller than anything we can currently measure. This is the realm of quantum gravity, where Einstein's relativity and quantum mechanics meet, and it's still largely theoretical. We don't have a complete theory of quantum gravity yet, but we're working on it. String theory, loop quantum gravity, and other approaches are attempting to unify these two great pillars of modern physics into a single coherent framework that describes how the universe works at every scale, from the smallest quantum fluctuations to the largest cosmic structures. If space is quantized, if it's made of discrete units, then the void itself has a structure at the Planck scale, about 10 to the power of minus 35 meters, a distance so small that it's meaningless to talk about anything smaller. At this scale, space might be a roiling foam of quantum fluctuations, a sea of virtual particles and temporary space-time geometries popping in and out of existence faster than anything can measure. The smooth, empty void we see at human scales would be an illusion, an average over countless quantum events happening at scales far too small for us to perceive. This has profound implications. If space itself is quantized, then it's not infinitely divisible. There's a smallest possible distance, a fundamental grain to reality. And if that's true, then our understanding of infinity, of continuity, of the nature of existence itself might need to be revised. The void might not be truly empty or truly continuous. It might be a discrete structure, a lattice or a network of fundamental units, and everything we see and experience might be emergent properties of this underlying quantum geometry. But we're getting ahead of ourselves. These are questions at the cutting edge of theoretical physics, and we don't have definitive answers yet. The void still has secrets, mysteries that we're only beginning to unravel, and that's exciting. That's what drives us forward, the knowledge that there's always more to learn, always deeper questions to ask, always new phenomena to discover. The universe is not a closed book. It's an ongoing story, and we're privileged to be reading it in real time. Let's come back to something more tangible, the actual contents of space. I've said that space is mostly empty, and that's true, but mostly is doing a lot of work in that sentence. Space does contain things, just very thinly distributed. There's the cosmic microwave background, that faint glow of photons left over from the Big Bang. There are cosmic rays, high-energy particles from supernovae and other violent events, constantly bombarding everything in space. There's the interstellar medium, a thin soup of gas and dust spread throughout the galaxy. There's the solar wind, a stream of charged particles flowing out from the sun. There are magnetic fields threading through space, shaping the behavior of charged particles. There are neutrinos, ghostly particles that barely interact with anything, streaming through space and through you right now by the trillions every second. And there's light, so much light. Every star in the universe is constantly emitting photons, and those photons travel through space at the speed of light until they're absorbed by something. Right now, you're being bathed in starlight from thousands of stars, photons that have traveled for years or decades or centuries just to reach your eyes at this moment. Most of that light is invisible to human eyes, infrared, ultraviolet, radio waves, X-rays, but it's there, filling space with electromagnetic radiation across the entire spectrum. So space is not truly empty. It's filled with photons and particles and fields, all of them interacting in complex ways. But the density is so low, the distances between particles so vast, that for practical purposes it might as well be empty. The interstellar medium, for instance, has a density of about 1 atom per cubic centimeter. That's 1 atom in a space the size of a sugar cube. In the voids between galaxies, the density drops to 1 atom per cubic meter or less. It's empty in a way that nothing on Earth can match, a vacuum so perfect that our best laboratory equipment can't come close to replicating it. But even that thin scattering of matter has effects. The interstellar medium blocks some wavelengths of light, making distant stars appear redder than they actually are. It provides the raw material for new stars, collapsing under its own gravity in molecular clouds to form protostars. It's enriched by supernova explosions, which scatter heavy elements across space, seeding future generations of stars and planets with carbon and oxygen and iron and all the other elements necessary for life. The interstellar medium is the ecosystem of the galaxy, the medium through which matter cycles, from star to supernova to nebula to new star, over and over again across billions of years. And in some places, the interstellar medium is not so thin. Molecular clouds, the densest regions of the interstellar medium, can have densities of thousands or even millions of particles per cubic centimeter. That's still incredibly thin by Earth standards. The air you're breathing has about 10 to the power of 19 particles per cubic centimeter, but it's enough for gravity to take hold, for the cloud to start collapsing, for stars to begin forming. These molecular clouds are the nurseries of the galaxy, the places where new stars are born, where planets form, where the next generation of solar systems comes into being. They're islands of relative density in an ocean of emptiness, oases in the cosmic desert. The most famous of these star-forming regions is the Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion. It's about 1,344 light-years away, and it's one of the most active star-forming regions in our neighborhood. Inside the nebula, dozens of young stars are being born, their light ionizing the surrounding gas and making it glow. It's a beautiful sight, a reminder that the void is not static, that it's constantly giving birth to new structures, new stars, new possibilities for life and consciousness. But most of space is not like the Orion Nebula. Most of space is the thin, cold interstellar medium, or the even thinner intergalactic medium, or the almost completely empty supervoids. Most of space is quiet, dark, and still, waiting patiently for something to happen, for some star to explode or some black hole to swallow matter or some galaxy to collide with another. The void is mostly boring if we're being honest. It's the objects within the void that are interesting, that capture our attention, that spark our imagination. The void itself is just the stage, the background against which the cosmic drama plays out. But that doesn't make it unimportant. Without the void, without the empty space between objects, the universe would be very different. Gravity would pull everything together into a single massive black hole. Stars wouldn't be able to form because the gas wouldn't have room to collapse. Galaxies wouldn't be able to separate and evolve independently. Life probably couldn't arise because planets would be constantly bombarded by radiation from nearby stars. The void, the emptiness, the distance between things, is what allows structure and complexity to exist. Paradoxically, it's the nothingness that makes the somethings possible. This is a profound idea. We tend to think of empty space as lacking value, as being uninteresting or unimportant. But the truth is that emptiness is just as essential to the universe as matter and energy. It's the canvas on which reality is painted, the silence between the notes that makes music possible, the negative space in a sculpture that gives the positive space its form and meaning. The void is not nothing. It's the foundation upon which everything is built. Let's talk about one more aspect of the void, its ultimate fate. I mentioned earlier that the universe will eventually enter a heat death, a state of maximum entropy where all the stars have died and all the black holes have evaporated, and all that's left is a thin soup of particles in an ever-expanding space. But there's another possibility depending on the nature of dark energy. If dark energy is truly constant, unchanging over time, then yes, we're headed for heat death. But if dark energy is increasing, if its strength is growing over time, then we might be headed for something called the Big Rip. In the Big Rip scenario, dark energy becomes so strong that it overcomes not just the expansion of space, but also the forces that hold structures together. First, galaxy clusters would be ripped apart, with galaxies flying away from each other faster than light. Then, galaxies themselves would be torn apart, stars scattering into the void. Then solar systems would disintegrate, planets flung away from their suns. Then planets themselves would be ripped apart, broken into smaller and smaller pieces. Eventually, even atoms would be torn apart, electrons stripped from nuclei, protons and neutrons broken into quarks. In the final moments before the Big Rip, space-time itself would be ripped apart, torn into quantum foam, and reality as we know it would cease to exist. Sounds terrifying, doesn't it? The good news is that the Big Rip, if it's going to happen at all, is tens of billions of years in the future, possibly much longer. We have time. The bad news is that we're not sure which scenario is correct. The nature of dark energy is still one of the biggest mysteries in cosmology. We know it's out there, pushing the universe apart, but we don't know what it is or how it behaves over time. Different theories predict different fates for the universe, and we won't know which one is correct until we can measure dark energy more precisely. There's also a third possibility, the Big Crunch. If there's enough matter in the universe, and if dark energy somehow decreases or reverses over time, then the expansion of the universe could slow down, stop, and reverse. The universe would start contracting, galaxies rushing back together, space itself shrinking. Eventually, everything would collapse back into a single point, a reverse Big Bang, ending in unimaginable heat and density. Some theories suggest this could lead to a new Big Bang, a cyclic universe that expands and contracts over and over again for eternity. But current observations suggest this is unlikely. The universe appears to be expanding forever, not contracting. So the most likely fate of the universe is heat death, an eternal expansion, cooling forever, becoming emptier and emptier until nothing remains but cold, dark space. It's not a comforting thought, but remember, this is trillions upon googles of years in the future. The universe still has a long, long life ahead of it before it reaches that final state. And who knows, maybe by then, if any form of intelligence still exists, they'll have found a way to survive, to create new universes, to escape the heat death somehow. Or maybe they'll have transcended the need for physical existence altogether, existing as pure information or energy or something we can't even imagine. The future is not written. We don't know what's possible. And that uncertainty, that openness to possibility, is its own kind of hope. In the meantime, we're here, now, in a universe that's full of stars and galaxies and mystery and wonder. We're alive in an age of discovery, when we're learning more about the cosmos than ever before, when we're taking our first steps beyond our home planet, when we're beginning to understand the fundamental laws that govern reality. We're part of something vast and ancient and beautiful, a universe that began in fire and will end in ice, but in between, in this brief cosmic moment, is full of light and life and consciousness. The cold emptiness of the universe is not the whole story. Yes, space is vast. Yes, it's mostly empty. Yes, it's cold and dark and hostile to life. But it's also full of stars and planets and galaxies and nebulae and black holes and neutron stars and all manner of exotic objects we're still discovering. It's governed by elegant laws of physics that we're gradually learning to understand. It has a history, a narrative arc from the Big Bang to the present to the far future. And somewhere in that vast expanse, on at least one tiny world orbiting one ordinary star, matter has organized itself into living, thinking beings who look up at the night sky and wonder about their place in it all. That's us. We're the universe's way of knowing itself. And that makes the void a little less empty, a little less cold, a little less lonely. Because we're here, together, asking these questions, seeking these answers, marveling at the strange and wonderful fact of our own existence in the midst of all this emptiness. So the next time you feel small or insignificant, the next time the vastness of space makes you feel like you don't matter, remember this: you're not separate from the universe. You're part of it. You're made of atoms that were forged in stars, powered by energy that came from the sun, animated by electrical signals in your brain that follow the same laws of physics that govern galaxies and black holes. You're a piece of the universe that has become conscious, that can think and feel and wonder. And that's extraordinary. That's miraculous. That's meaningful. The void is vast, but we contain multitudes. The universe is cold, but we are warm. The darkness is deep, but we carry light within us. We are the universe's answer to its own emptiness, its rebellion against the second law of thermodynamics, its way of saying that matter matters, that consciousness counts, that meaning can emerge from meaninglessness. We are brief, yes. We are fragile. We are temporary. But we are here. And that's everything. This journey into the void, this exploration of the cold emptiness of space, is really a journey into ourselves, into the nature of existence, into the question of what it means to be a conscious being in an indifferent universe. And the answer, I think, is this: it means we get to choose. We get to decide what matters, what's important, what's worth doing with the brief time we have. The universe doesn't give us meaning. We create it. We make our own purpose in a purposeless cosmos. And that's not a burden. That's a freedom. That's an opportunity. So look up at the stars. Feel the vastness of space, the cold of the void, the ancient light of distant suns. Let yourself feel small in the face of that immensity. And then remember that you're not just a passive observer. You're a participant. You're part of the story. You're one of the ways the universe is exploring itself, understanding itself, experiencing itself. The void is out there, vast and cold and empty, but you're in here, warm and alive and full of possibility. And that makes all the difference. The cold emptiness of the universe is real. It's the dominant feature of the cosmos, the default state of existence. But it's not the final word. We are. Life is. Consciousness is. We've emerged from the void. and we carry within us the capacity to fill it with meaning, with purpose, with light. That's the real journey, not just out into space, but inward into our own nature, into the question of who we are and what we're capable of becoming. The universe has given us an incredible gift, the chance to exist, to experience, to understand. And our gift back to the universe is to do something with that chance, to make it count, to ensure that the light of consciousness continues to burn, however briefly, against the eternal darkness. This is the cold emptiness of the universe, and this is our place within it. Tiny, brief, improbable, and precious beyond measure. We are the universe waking up, looking around, and deciding that existence is better than non-existence, that light is better than darkness, that warmth is better than cold. We are the rebellion. We are the hope. We are the meaning in the void. And as long as we're here, as long as we continue to wonder and explore and create and love, the universe is not just cold and empty. It's alive with possibility. It's filled with wonder. It's home. Now, let me take you deeper into the mathematics of emptiness, because numbers tell a story that words alone cannot capture. The observable universe has a radius of about 46.5 billion light-years. That's a sphere with a volume of roughly 4 by 10 to the power of 80 cubic meters. Within that volume, there are an estimated 2 trillion galaxies, each containing anywhere from a few million to several trillion stars. Let's be conservative and say there are 100 billion stars per galaxy on average. That gives us 2 by 10 to the power of 23 stars in the observable universe. That's 200 billion trillion stars. Sounds like a lot, and it is. But now let's calculate how much space each star gets, on average. If we divide the volume of the observable universe by the number of stars, each star gets about 2 by 10 to the power of 57 cubic meters of space to itself. To put that in perspective, that's a cube about 800 million light-years on each side. 800 million light-years for each star. That's how empty the universe is. Each star, on average, is separated from its neighbors by distances so vast that light takes hundreds of millions of years to cross them. And remember, stars aren't evenly distributed. They're clumped into galaxies, which are clumped into clusters, which are arranged in filaments around vast voids. So in reality, some stars have neighbors just light years away, while others, in the voids, might be billions of light years from the nearest significant concentration of matter. Let's think about density another way. The average density of the universe is about 10 to the power of minus 27 kilograms per cubic meter. That's 0.000000000000000000000000000001 kilograms per cubic meter. For comparison, air at sea level has a density of about 1.2 kilograms per cubic meter. Water has a density of 1,000 kilograms per cubic meter. Even the best laboratory vacuums we can create have densities of about 10 to the power of minus 17 kilograms per cubic meter. The universe is 10 billion times less dense than our best vacuums. It's empty in a way that strains our ability to comprehend. And yet, within this near-perfect vacuum, complex structures form. Galaxies rotate, stars burn, planets orbit, life emerges. How is this possible? The answer is gravity. Gravity, the weakest of the 4 fundamental forces, is also the only one that always attracts, never repels. It's also the only force that acts over unlimited distances. Electromagnetic forces cancel out at large scales because there are equal amounts of positive and negative charge. Strong and weak nuclear forces only act over distances smaller than an atomic nucleus. But gravity just keeps adding up. Every particle of matter attracts every other particle, however weakly. And over cosmic scales, that adds up to something significant. This is how structure forms in the void. Start with tiny fluctuations in density, the quantum variations imprinted during inflation. These create regions where gravity is slightly stronger. Matter flows toward these regions, making them denser still, which increases their gravity, which attracts more matter. It's a runaway process, a cosmic snowball effect. Over billions of years, these initial tiny fluctuations grow into the galaxies and galaxy clusters we see today, separated by voids where the density is even lower than the cosmic average. But gravity isn't the only force shaping the void. Dark energy, that mysterious repulsive force, is pushing space itself apart, causing the expansion of the universe to accelerate. On small scales, inside galaxies and galaxy clusters, gravity wins. The mutual attraction of all that matter is strong enough to overcome the expansion. But on larger scales, in the voids between clusters, dark energy dominates. It's stretching space, pushing the clusters apart, making the voids grow larger and emptier. In the far future, dark energy will win everywhere. Galaxies that aren't gravitationally bound to each other will be pushed apart, receding beyond each other's cosmic horizons, disappearing from view forever. The universe will become lonelier, emptier, darker. But that's still billions of years away. For now, we live in an age of relative abundance, when galaxies are close enough to see, when stars are still being born, when the universe is full of light and activity. It's a golden age, cosmically speaking, and we should appreciate it while it lasts. Because it won't last forever. Nothing does. The second law of thermodynamics, the law that says entropy always increases, guarantees that the universe is running down, moving from order to disorder, from complexity to simplicity, from hot to cold. It's an inevitable process, as certain as death and taxes, as fundamental as the laws of physics themselves. This might sound depressing, but there's a strange comfort in it too. The fact that everything ends means that everything that exists now is temporary, precious, unique. The stars will die, yes, but right now they're shining. Galaxies will disperse, yes, but right now they're full of wonder. We will die, yes, but right now we're alive. The impermanence of things doesn't diminish their value. It enhances it. We don't mourn the ending of a beautiful song. We appreciate it while it plays. The universe is the same. It's temporary, fleeting, but right now, in this cosmic moment, it's glorious. Let's talk about black holes, those ultimate expressions of gravitational collapse. Those points of infinite density hidden behind event horizons. Black holes are, in a sense, the opposite of the void. Where the void is empty, black holes are full to bursting with matter compressed into an infinitesimal space. Where the void is cold, black holes are surrounded by infalling matter heated to billions of degrees. Where the void is unchanging, black holes are dynamic, growing as they consume matter, spinning, merging, sending out gravitational waves. And yet, black holes are also intimately connected to the void, because they represent its ultimate victory. Matter falls into a black hole and, from our perspective, disappears from the universe. It crosses the event horizon and is lost forever, adding to the black hole's mass but contributing nothing else to the cosmos. The black hole grows, but the information about what fell in is lost. Or is it? This is the black hole information paradox, one of the deepest puzzles in theoretical physics. Quantum mechanics says that information cannot be destroyed. If you know the exact quantum state of a system at one time, you can in principle calculate its state at any other time. But black holes seem to violate this principle. They swallow information and don't give it back. When a black hole eventually evaporates through Hawking radiation, the radiation appears to be random, containing no information about what fell in. So where does the information go? Is it destroyed, violating quantum mechanics? Is it stored somehow in the black hole or the radiation? Does it escape in some way we don't understand? Physicists have been debating this for decades, and we still don't have a definitive answer. Stephen Hawking initially argued that information was destroyed, that black holes were an exception to the rules of quantum mechanics. Later, he changed his mind, proposing that information might be encoded in the event horizon itself or released in subtle correlations in the Hawking radiation. Other physicists have suggested that information might escape through wormholes, or that black holes might transform into white holes that spit the information back out, or that our entire understanding of space and time breaks down at the event horizon and we need a new theory to describe what really happens. The debate continues, and it's not just academic. Resolving the information paradox might give us clues about how to unify quantum mechanics and general relativity, the two great theories of modern physics that seem to contradict each other in extreme conditions like black holes and the Big Bang. But let's step back from the theoretical for a moment and think about what black holes mean for the void. They're the final resting place for matter, the endpoints of gravitational collapse. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses, and if it's massive enough, nothing can stop the collapse. The core shrinks past the point where neutron degeneracy pressure can hold it up, past the point where any known force can provide resistance. It collapses all the way to a singularity, a point of infinite density, and an event horizon forms around it, trapping everything inside. The black hole is born. Once formed, a black hole is remarkably simple. It has mass, charge, and angular momentum, and that's it. No other properties. This is summed up in the phrase, black holes have no hair, meaning they have no distinguishing features beyond these three numbers. Two black holes with the same mass, charge, and spin are identical, regardless of what fell into them to make them. All the complexity of the matter that formed the black hole is lost, erased, hidden behind the event horizon. In this sense, black holes are the ultimate simplifiers, reducing complexity to three numbers and a horizon. And they're common. Our galaxy alone is estimated to contain about 100 million stellar mass black holes, the remnants of massive stars that died in supernova explosions. At the center of our galaxy, and indeed at the center of most large galaxies, there's a supermassive black hole, millions or billions of times the mass of the Sun Sagittarius A-. The supermassive black hole at the center of the Milky Way has a mass of about 4 million solar masses. It's surrounded by a swarm of stars orbiting at incredible speeds, some completing an orbit in just a few years. We've watched these stars for decades, mapping their orbits, and they provide the strongest evidence we have that Sagittarius A is indeed a black hole. Nothing else could have so much mass in such a small space. In 2019, we took the first ever image of a black hole, or rather, the shadow of its event horizon against the glowing matter surrounding it. The Event Horizon Telescope, a network of radio observatories around the world working together as a single Earth-sized telescope, captured an image of the supermassive black hole at the center of the galaxy M87. The image shows a dark circle, the shadow of the event horizon, surrounded by a glowing ring of hot gas spiraling into the black hole. It's a stunning achievement, confirmation that black holes really do exist as general relativity predicts, that event horizons are real, that Einstein was right again. But black holes don't just sit there passively. They grow by consuming matter, and when they do, they can release enormous amounts of energy. Matter falling into a black hole accelerates to near the speed of light, colliding with other particles and heating up to billions of degrees. This hot, glowing disk of matter, called an accretion disk, emits radiation across the spectrum, from radio waves to X-rays. Some black holes, particularly supermassive ones at the centers of active galaxies, are surrounded by so much infalling matter that they shine brighter than entire galaxies. These are quasars, the most luminous objects in the universe, visible across billions of light years. A quasar can outshine 1 trillion stars, all powered by matter falling into a black hole no larger than our solar system. And then there are the jets. Some black holes, particularly those that are rapidly spinning, launch enormous jets of particles and radiation perpendicular to the accretion disk. These jets can extend for millions of light years, carrying energy and momentum far out into intergalactic space, heating the surrounding gas, triggering star formation in some regions and suppressing it in others. The jets are powered by the rotation of the black hole itself, extracting energy from its spin through a process discovered by Roger Penrose. As matter falls into the black hole and circles around it in the accretion disk, The black hole's intense gravity and frame-dragging effects can accelerate some of that matter to nearly the speed of light and fling it outward in narrow beams. It's one of the most efficient energy conversion processes in the universe, converting up to 42% of infalling matter's mass into energy, far more efficient than nuclear fusion, which converts less than 1%. Black holes are also mergers. When two black holes orbit each other, they emit gravitational waves, losing energy and spiraling closer together. Eventually, they merge, combining their masses into a single, larger black hole. The final moments of this merger are violent, releasing more energy in gravitational waves than all the stars in the observable universe emit in light. The merged black hole rings like a bell, its event horizon vibrating with characteristic frequencies that we can detect with observatories like LIGO and Virgo. These ring-down signals tell us about the mass and spin of the newly formed black hole, confirming that it behaves exactly as general relativity predicts. And in the far future, after the last stars have died and the universe has entered the black hole era, black holes will be the dominant objects in the cosmos. They'll slowly evaporate through Hawking radiation, a quantum effect where virtual particle pairs form near the event horizon, and one particle falls in while the other escapes. The escaping particles carry away energy, very slowly reducing the black hole's mass. For a stellar mass black hole, this process takes about 10 to the power of 67 years. For a supermassive black hole, it takes 10 to the power of 100 years or more. These timescales are so long that they make the current age of the universe look like a blink of an eye. But eventually, given enough time, even the largest black holes will evaporate completely, leaving behind nothing but a final burst of radiation and a slightly warmer void. This brings us to the ultimate fate of matter itself. Protons, the building blocks of atomic nuclei, might not be stable. Some theories in physics predict that protons eventually decay, breaking down into lighter particles. The experiments we've done so far haven't detected proton decay, which means if it happens, it must be incredibly rare. The lower limit on the proton lifetime is about 10 to the power of 34 years. That's 10 million billion years. But if protons do decay even on such timescales, then eventually all matter will break down. Atoms will disintegrate. The dead remnants of stars, white dwarfs, neutron stars will slowly dissolve. Even the matter inside black holes, though we can't observe it, would presumably decay as well. In the ultimate end, trillions upon trillions of years in the future, even matter itself might vanish, leaving behind only photons and leptons and perhaps dark matter particles, if they're stable, scattered across an ever-expanding void. This is the true heat death of the universe. Not just the death of stars and the evaporation of black holes, but the potential dissolution of matter itself. The universe would become a faint mist of particles and photons, cooling forever as space expands, approaching but never quite reaching absolute zero. At that point, nothing would happen anymore. No stars would form, no structures would arise, no complexity would emerge. The universe would be in a state of thermodynamic equilibrium, maximum entropy, where every part of the universe has the same temperature and the same density and nothing drives any changes. It would be the end of history, the end of process, the end of everything we recognize as existence. Just cold, dark, empty space, expanding forever, growing colder and emptier and darker with each passing eon. But here's a thought to wrestle with: we don't know for certain that this is how it will end. Our understanding of physics might be incomplete. There might be phenomena we haven't discovered yet, processes we can't predict, structures that form on timescales we can't imagine. The universe has surprised us before. A century ago, we didn't know about dark matter or dark energy or gravitational waves or quantum mechanics. Who knows what we'll discover in the next century or the next millennium? Maybe there are ways to avoid heat death, to create new structures even in a cold, expanding universe. Maybe intelligent beings in the far future will find ways to survive, to extract energy from the vacuum itself or from the quantum fluctuations that never quite disappear. Maybe they'll learn to create new universes, baby universes budding off from ours, carrying life and consciousness into new realms of existence. Or maybe not. Maybe heat death really is inevitable, the ultimate fate of everything. But we don't know, and that uncertainty is its own kind of hope. Let's talk about the scale of time because it's just as mind-boggling as the scale of space. The universe is 13.8 billion years old. That seems like a long time, and by human standards, it is. But compare it to the timescales of the far future. The last star will burn out in about 100 trillion years. That's about 7,000 times longer than the current age of the universe. The black hole era, when black holes dominate, will last until about 10 to the power of 100 years. That's a googol years, a number so large that if you wrote it out in full, you'd have a 1 followed by 100 zeros. The number of atoms in the observable universe is only about 10 to the power of 80. There are more years in the black hole era than there are atoms in the entire observable universe. And if protons decay, the photon era, when even black holes have evaporated and only photons and leptons remain, could last until 10 to the power of 10 to the power of 56 years. That's not a typo. That's 10 to the power of 10 to the power of 56. It's a number so large that it doesn't fit in standard notation. You'd need exponential towers just to write it down. It's larger than any physical quantity we've ever measured or calculated. It's larger than the number of possible quantum states in the observable universe. It's a number that, for all practical purposes, might as well be infinity. Compared to these timescales, the age of the universe so far is nothing. We're in the earliest moments of cosmic history, the opening seconds of a movie that will last for googols of years. Almost all of the universe's future is still ahead of it, and almost all of that future will be cold, dark, and empty. The stelliferous era, the age of stars, is just a brief flash at the beginning, a moment of warmth and light before the long darkness. We're incredibly fortunate to be living in this moment, to be here when stars are shining and galaxies are visible and complexity is possible. In the grand scheme of things, we're at the right place at the right time. Later would be worse, much worse. This perspective can be humbling, but it can also be empowering. We exist during the universe's brief moment of glory, its time of maximum interest and complexity. We're part of the peak, the apex, the best the universe has to offer. And we're not just passive observers. We're active participants, conscious beings who can appreciate the universe's beauty, understand its laws, and perhaps even influence its future in small ways. We can't stop the heat death or prevent the eventual cooling of the cosmos, but we can make the most of the time we have. We can learn, create, love, explore. We can send messages to the stars, build monuments that outlast us, pass our knowledge to future generations. We can make our brief moment matter. And who knows, maybe in the far future, when the universe is cold and dark, some remnant of humanity or its descendants will still exist, huddled around the last sources of energy, keeping the flame of consciousness alive against the dying of the light. Maybe they'll remember us, the ancients who lived when stars were young and galaxies were bright, who took the first steps into space and asked the first questions about the nature of existence. Maybe they'll look back on our time with nostalgia, the way we look back on childhood, a time of warmth and light and possibility before the cold reality of adulthood sets in. Or maybe they won't. Maybe we'll be forgotten, our entire civilization erased by time, our monuments crumbled, our messages lost. But that doesn't make what we do now meaningless. The fact that something ends doesn't diminish its value while it lasts. Let me tell you about the loneliest object in the universe. It's called HD 140283, also known as Methuselah, and it's a subgiant star about 190 light-years from Earth. What makes it special is its age. It's about 14.5 billion years old, give or take 0.8 billion years. Wait, you might say, didn't you tell me the universe is only 13.8 billion years old? How can a star be older than the universe? The answer is that it's not quite. The error bars on Methuselah's age overlap with the age of the universe, so it's consistent with physics. But it's cutting it close. Methuselah formed very early in the universe's history, probably within the first few 100 million years after the Big Bang. It's one of the oldest objects we know of, a survivor from the cosmic dawn, still shining today. Methuselah is metal poor, meaning it has very few elements heavier than helium. That's because it formed before many generations of stars had lived and died, before supernovae had scattered heavy elements across space. It's made almost entirely of the primordial hydrogen and helium that came out of the Big Bang. Looking at Methuselah is like looking at a fossil from the universe's childhood, a survivor from a time when the cosmos was young and mostly empty, when the first stars were just beginning to light up the darkness. Think about what Methuselah has witnessed. It was shining when the first galaxies were forming, when the universe was still full of primordial gas clouds collapsing under their own gravity. It was there when the Milky Way was just beginning to take shape, when our galaxy was a chaotic mess of merging protogalactic fragments. It watched as generations of stars were born and died around it, as supernovae enriched the interstellar medium with heavy elements, as planetary systems formed and evolved. It's been burning steadily for nearly the entire history of the universe, and it's still here, still visible, still teaching us about the early cosmos. That's persistence. That's endurance. That's a testament to the power of nuclear fusion and the longevity of low-mass stars. But Methuselah won't last forever. Eventually, in another few billion years, it will exhaust its hydrogen fuel and expand into a red giant, then shed its outer layers and collapse into a white dwarf. Even the oldest stars die eventually. Nothing escapes the second law of thermodynamics. But before it dies, Methuselah will have lived for perhaps 20 billion years, twice the current age of the universe. It will have seen things we can only imagine: the evolution of galaxies, the changing structure of the cosmos, perhaps even the emergence and extinction of countless civilizations on countless worlds. If stars could remember, if they could tell stories, what tales Methuselah would have to tell. Now let's shift our perspective and talk about the things that fill the void, the particles and fields that permeate what we call empty space. I mentioned earlier that space contains the cosmic microwave background, cosmic rays, photons, and neutrinos. But there's more. Space is threaded with magnetic fields, invisible lines of force that shape the behavior of charged particles. These fields are generated by stars, by planets with molten cores like Earth, by the accretion disks around black holes, by the movement of charged particles in the interstellar and intergalactic medium. They're everywhere, connecting different regions of space, creating pathways along which matter and energy can flow. The Sun, for instance, has a magnetic field that extends far beyond the visible surface of the star, reaching out into interplanetary space and beyond. This magnetic field is carried by the solar wind, a stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. The solar wind creates a bubble around the solar system called the heliosphere, a region where the Sun's influence dominates. At the edge of the heliosphere, about 120 astronomical units from the Sun, the solar wind finally runs into the interstellar medium, the thin gas between stars. This boundary is called the heliopause, and it's where the Sun's domain ends and true interstellar space begins. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. It's now about 150 astronomical units from the Sun, traveling at 38,000 miles per hour relative to the Sun. At that speed, it's covering the distance from Earth to the Moon in about 15 hours. Sounds fast, right? But at that rate, it would still take Voyager 1 more than 70,000 years to reach the nearest star. That's how vast the void between stars is. Even our fastest spacecraft, traveling for decades, has barely made a dent in the distance. Voyager 1 is in interstellar space, yes, but it's still in the Sun's neighborhood, cosmically speaking. It's like walking to the end of your driveway and saying you've left the city. True, technically, but you've got a long way to go before you reach anywhere else. Interstellar space is different from the space within the solar system. It's colder, darker, emptier. The density of matter is lower, the radiation environment is different, the magnetic fields are weaker. Voyager 1's instruments have detected subtle changes in the plasma around it, the cosmic rays, the magnetic field orientation. These measurements are giving us our first direct look at the interstellar medium, the stuff between the stars. And what we're finding is that it's not uniform. It has structure, variations in density and temperature and composition. Some regions are hotter, heated by shock waves from supernova explosions. Some are denser concentrations of gas and dust that will eventually collapse to form new stars. Some are magnetized, threaded with field lines that guide the motion of charged particles. The void is not a featureless expanse. It's textured, varied, full of subtle complexities that we're only beginning to understand. Let's talk about cosmic rays, because they're one of the most energetic phenomena in the void. Cosmic rays are not actually rays. They're particles, mostly protons, but also heavier nuclei and even some electrons and positrons, traveling through space at nearly the speed of light. They're accelerated to these incredible energies by violent events like supernova explosions, by the shock waves from those explosions propagating through the interstellar medium, by the intense magnetic fields around neutron stars and black holes. The most energetic cosmic rays have energies of 10 to the power of 20 electron volts or more. That's the energy of a baseball traveling at 60 miles per hour, concentrated in a single subatomic particle. It's an absurd amount of energy for something so small. Where do these ultra-high energy cosmic rays come from? We're not entirely sure. Supernova remnants can accelerate particles to high energies, but probably not to the highest energies we observe. Those might come from active galactic nuclei, the supermassive black holes at the centers of galaxies, or from some other exotic source we haven't identified yet. Detecting cosmic rays is tricky because they're charged particles, and charged particles are deflected by magnetic fields. By the time a cosmic ray reaches Earth, it's been bounced around by the galactic magnetic field so much that we can't trace it back to its source. It's like trying to figure out where a pinball came from by watching where it ends up. The path is too random, too chaotic. When cosmic rays hit Earth's atmosphere, they collide with atoms in the air, creating showers of secondary particles that cascade down to the ground. These air showers can contain billions of particles, spread over several square kilometers. We detect them using arrays of detectors on the ground, which measure the arrival times and energies of the particles. By reconstructing the shower, we can infer the energy and direction of the original cosmic ray. The Pierre Auger Observatory in Argentina, for instance, covers an area of 3,000 square kilometers with 1,600 detector stations, all working together to catch these rare, high-energy events. And they are rare. The highest energy cosmic rays might hit any given square kilometer of Earth's atmosphere only once per century. We need big detectors and a lot of patience to find them. But why should we care about cosmic rays? Because they tell us about the most violent, energetic processes in the universe. They tell us about supernova explosions, about relativistic jets from black holes, about the acceleration mechanisms in shock waves and magnetic reconnection events. They tell us about the structure of the galactic magnetic field, because the paths of cosmic rays are shaped by that field. They even affect the chemistry of Earth's atmosphere and might influence cloud formation and climate. Cosmic rays are messengers from the void, carrying information about distant, energetic events, and we're learning to read their messages. Now, imagine you're a photon, a particle of light, born in the core of a star. You're created in a nuclear fusion reaction, a proton-proton chain, or a CNO cycle, deep in the star's heart where temperatures reach millions of degrees. You start your journey toward the surface, but it's not a straight path. The star's interior is dense, packed with other particles, and you constantly collide with electrons, getting absorbed and re-emitted, scattered in random directions. Each collision changes your energy, your direction, your path. This random walk through the star's interior is called radiative diffusion, and it's slow, incredibly slow. It takes a photon somewhere between 100,000 and a million years to diffuse from the core of the sun to its surface, even though the straight-line distance is only about 700,000 kilometers. which light could cross in 2.3 seconds. But eventually, you make it. You reach the surface, the photosphere, where the density drops enough that you can escape into space without being absorbed again. You're free. You shoot away from the star at the speed of light, traveling through the void. If you're headed toward Earth, you'll arrive in about 8 minutes and 20 seconds, having crossed 150 million kilometers of near-perfect vacuum without encountering a single obstacle. You might hit a dust grain or a gas molecule, but probably not. Space is so empty that you're likely to travel all the way to Earth without interacting with anything. And when you arrive, you might hit a leaf on a tree, driving photosynthesis, or a solar panel generating electricity, or someone's retina, allowing them to see. You, a photon born 100,000 years ago in the core of the sun, have finally completed your journey. Or maybe you're not headed toward Earth. Maybe you're headed out into the void, away from any planets or stars. You'll travel for years, decades, centuries, millennia, crossing light years of empty space. You might pass through molecular clouds, getting absorbed and re-emitted, your energy slightly reduced. You might encounter other photons, though the probability is vanishingly small. You might travel for millions or billions of years, crossing entire galaxies until finally you hit something. A planet, a star, a grain of dust, a detector on some distant spacecraft built by some alien civilization. Or maybe you never hit anything. Maybe you travel forever through an ever-expanding universe, becoming more and more redshifted as space stretches, your energy decreasing, your wavelength lengthening, until you're a radio wave, then a microwave, then something even longer. Eventually, in the far future when the universe is cold and empty, you'll be just one more photon in the faint glow of the cosmic background, indistinguishable from all the others, your history lost, your origin forgotten. This is the journey that light makes through the void, and it's a journey that connects us to the cosmos. Every photon that enters your eye has traveled across space to reach you, carrying information about where it came from, what it interacted with along the way. The light from the sun tells us about the sun's composition, temperature, magnetic fields. The light from distant stars tells us about those stars, and also about the interstellar medium it passed through. The light from distant galaxies tells us about those galaxies, their motion, their distance, their age. Light is our primary tool for understanding the universe, and the void is the medium through which that light travels. But light isn't the only messenger. Neutrinos, those ghostly particles I mentioned earlier, are another way we observe the universe. Neutrinos are produced in nuclear reactions, both in stars and in more violent events like supernovae. They're also produced in the early universe, and there's a cosmic neutrino background similar to the cosmic microwave background, though we haven't detected it yet because neutrinos interact so weakly with matter. A neutrino can pass through a light year of lead without being absorbed. They pass through the Earth like it's not even there. Trillions of neutrinos from the sun pass through your body every second, and you never notice because they almost never interact with your atoms. But almost never is not the same as never. Very occasionally, a neutrino will interact with an atom, and we can detect that interaction if we're looking for it. Neutrino detectors are huge tanks of ultra-pure water or other materials, buried deep underground to shield them from cosmic rays and other background radiation. When a neutrino interacts with an atom in the detector, it produces a charged particle that moves faster than light moves through water, creating a shockwave of light called Cherenkov radiation. Sensitive photomultiplier tubes lining the walls of the detector pick up this faint flash of light, and we can reconstruct where the neutrino came from and what its energy was. The most famous neutrino observation came in 1987, when a star exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 168,000 light-years away. This was supernova 1987A, and it was visible to the naked eye, the first supernova that bright in nearly 400 years. But before the light from the explosion reached Earth, the neutrinos did. Neutrino detectors in Japan and the United States detected a burst of about 24 neutrinos, all arriving within a few seconds of each other. These neutrinos had been produced in the collapsing core of the dying star, and they escaped hours before the light did because neutrinos don't interact with the star's outer layers. They just fly straight through, carrying the news of the core collapse with them. Those couple dozen neutrinos, detected 168,000 years after they were produced, confirmed our theories of how supernovae work and opened a new window on the universe. Neutrino astronomy was born. Since then, we've detected neutrinos from the sun, from the atmosphere, from cosmic ray interactions, and from distant blazars and other extreme objects. We're building bigger, more sensitive neutrino detectors to catch more of these elusive particles. IceCube, a neutrino telescope embedded in the ice at the South Pole, uses a cubic kilometer of ice as its detector volume. Antares, in the Mediterranean Sea, uses seawater. Future detectors will be even larger, giving us better views of the neutrino sky. And what we're learning is that neutrinos carry information that light cannot. They tell us about the cores of stars, about the mechanisms of supernovae, about the acceleration of cosmic rays, about processes happening in environments so dense and hot that light can't escape. Neutrinos are another messenger from the void, complementing light and gravitational waves, filling in pieces of the cosmic puzzle. Speaking of which, let's revisit gravitational waves, because they're revealing aspects of the void that we never knew existed. Since that first detection in 2015, LIGO, Virgo, and now CAGRA have detected dozens of gravitational wave events. Most of them are from merging black holes, but we've also detected merging neutron stars, and even what appears to be a black hole swallowing a neutron star. Each event tells us something about the population of compact objects in the universe, about how often they merge, about their masses and spins. We're learning that black hole mergers are common, that neutron star mergers might be the source of most of the heavy elements in the universe, that the void is more active and violent than we realized. Gravitational wave detections have also confirmed some predictions of general relativity with stunning precision. The black holes ring after they merge, vibrating like a struck bell, and the frequencies of those vibrations match Einstein's predictions to better than 1%. The waves travel at exactly the speed of light, not faster or slower. The waveforms match the computer simulations we've run based on general relativity. Every test confirms that Einstein was right, that space-time really does curve and ripple and vibrate according to his equations. It's one of the great triumphs of human intellect that a theory developed a century ago based on pure thought and mathematics describes reality with such precision. But gravitational waves also hint at mysteries. Some of the black holes we've detected are more massive than we expected, heavier than stellar collapse should produce. Where did they come from? Are they the products of previous mergers, black holes that have grown by consuming other black holes? Are they primordial black holes, formed in the early universe rather than from dying stars? We don't know yet. We're also searching for gravitational waves from other sources. Spinning neutron stars with mountains on their surfaces, cosmic strings, hypothetical defects in space-time from the early universe, maybe even the Big Bang itself. The primordial gravitational wave background, if we can detect it, would tell us about the first fraction of a second of the universe's existence, about inflation, about the conditions when time itself began. This brings us to one of the deepest questions in cosmology. What is time? We experience time as a flow, a river carrying us from past to future, from birth to death. But physics doesn't really support that view. In relativity, time is just another dimension, like space, and the past and future both exist, laid out in a four-dimensional spacetime. The now that we experience is not fundamental. It's a subjective perception, a feature of our consciousness rather than a feature of the universe. Different observers moving at different speeds will disagree about what events are simultaneous, about what's happening now. Time is relative, malleable, dependent on motion and gravity. Near a black hole, time slows down. If you could hover just above the event horizon of a supermassive black hole and watch the outside universe, you'd see time speed up. Stars would live and die in what seems like moments. Galaxies would evolve in fast forward. If you stayed there long enough, though you couldn't, because the tidal forces would destroy you, You could watch the entire future of the universe play out before your eyes. Meanwhile, to observers far from the black hole, you'd appear to be moving in slow motion, your clock ticking slower and slower as you approach the event horizon, until finally you seem to freeze, asymptotically approaching the horizon but never quite crossing it. This time dilation is real and measurable. Atomic clocks in satellites orbiting Earth run slightly faster than atomic clocks on the ground because they're higher in Earth's gravitational field. GPS satellites have to account for this effect, correcting for both the gravitational time dilation and the special relativistic time dilation due to their orbital speed. Without these corrections, GPS would accumulate errors of several kilometers per day. The fact that GPS works is proof that relativity is correct, that time really does run at different rates in different places. But what about the arrow of time, the fact that time seems to flow in only one direction? Why do we remember the past but not the future? Why does cause precede effect? Why do eggs break but never spontaneously unbreak? The answer lies in entropy, the second law of thermodynamics. Entropy is a measure of disorder, and the second law says that entropy always increases in a closed system. This gives time its direction. The past is the direction of lower entropy, the future is the direction of higher entropy. We remember the past because memories are low-entropy structures in our brains, and creating them increases the entropy of the universe overall. We can't remember the future because high-entropy states don't contain the information needed to reconstruct low-entropy states. But why was the entropy so low in the past? Why did the universe start in a highly ordered state? The Big Bang was not a chaotic explosion but a remarkably uniform, smooth, low-entropy beginning. The cosmic microwave background shows this. It's the same temperature everywhere to 1 part in 100,000. That's an incredibly ordered state. As the universe evolved, gravity amplified the tiny fluctuations in density, creating structure, stars, galaxies, clusters. But creating structure locally increases entropy globally. Stars burn hydrogen, converting low-entropy fuel into high-entropy waste heat and light. Black holes form maximal entropy objects. The universe is running down, becoming more disordered, more uniform, more empty. The arrow of time points toward heat death, toward maximum entropy, toward the cold, dark, empty void. And yet, here we are, living in a temporary pocket of low entropy, a brief deviation from the universe's march toward disorder. Life itself is a low-entropy phenomenon, maintaining order at the expense of increasing the entropy of its surroundings. Every time you eat, you're consuming low-entropy food, organized molecules, and excreting high-entropy waste. Every time you think, your brain is processing information, maintaining its complex structure, while generating heat that increases the entropy of the universe. You're a thermodynamic anomaly, a rebellion against entropy, a brief spike of order in a universe trending toward disorder. And that's beautiful. That's what makes life special, what makes consciousness precious. We're fighting against the fundamental direction of time itself, and for a while, we're winning. Let me take you on a journey through the cosmic timeline, from the Big Bang to the far future, focusing on how the void evolves. In the beginning, there was no void. The universe was dense and hot, filled with a plasma of quarks and gluons, then protons and neutrons, then nuclei and electrons. Space itself was tiny, compressed into a region smaller than an atom. Then inflation happened, a period of exponential expansion that stretched space by a factor of at least 10 to the power of 26 in a fraction of a second. After inflation, the universe was enormous and mostly empty, but still hot, still filled with radiation. Over the next 380,000 years, the universe expanded and cooled until atoms could form and light could travel freely. This is when the cosmic microwave background was created, the afterglow we still see today. As the universe continued to expand and cool, the void grew. Matter became more dilute, spread thinner across ever larger volumes of space. But gravity was at work, pulling matter together in regions where the density was slightly higher. These regions collapsed, forming the first stars about 100 to 200 million years after the Big Bang. These first stars were massive, made only of hydrogen and helium, burning hot and bright and dying young in spectacular supernova explosions. Those explosions scattered heavy elements across space, enriching the interstellar medium, enabling the formation of later generations of stars and eventually planets like Earth. Over billions of years, galaxies formed, merged, evolved. The cosmic web took shape, filaments of galaxies surrounding vast voids. The universe we see today, 13.8 billion years after the Big Bang, is the product of this evolution. But it's still young, cosmically speaking. We're still in the stelliferous era, when stars are actively forming and burning. This era will last for another 100 trillion years or so, until the last of the hydrogen and helium has been converted into heavier elements or locked up in dead stellar remnants. After that comes the degenerate era, when the only objects left are cold white dwarfs, brown dwarfs, neutron stars, and black holes. No more stars shine. The universe is dark, lit only by the occasional flare when two brown dwarfs collide or a dead star falls into a black hole. This era lasts from about 10 to the power of 14 years to 10 to the power of 40 years. By the end of it, even the white dwarfs and neutron stars have decayed, if proton decay is real, or been consumed by black holes. Then comes the black hole era, from 10 to the power of 40 years to 10 to the power of 100 years. The universe is dominated by black holes, which slowly evaporate through Hawking radiation. Smaller black holes evaporate first, larger ones take longer. Eventually, even the supermassive black holes at the centers of galaxies disappear, leaving behind only photons and neutrinos and perhaps some exotic particles we haven't discovered yet. Finally, the dark era or the photon era begins. This is the true heat death, when the universe is cold and dark and almost perfectly uniform. The temperature approaches absolute zero as space continues to expand, diluting what little energy remains. On timescales of 10 to the power of 10 to the power of 56 years or more, even this state might not be stable. Quantum tunneling events, incredibly rare but given enough time inevitable, might cause matter to spontaneously reorganize. Particles might tunnel through energy barriers, rearranging into different configurations. Some physicists have speculated that, given enough time, a Boltzmann brain could spontaneously fluctuate into existence. A random assembly of particles that just happens to form a conscious mind, complete with false memories of a past that never existed. These would be the new observers, in an otherwise dead universe, brief sparks of consciousness in an infinite void, existing for a moment before dissipating back into randomness. But even these bizarre possibilities assume that the laws of physics as we understand them continue to hold. And we don't know that they will. Over such vast timescales, things we think are impossible might become possible. New physics might emerge. The vacuum itself might decay into a lower energy state, a process that would destroy everything and rewrite the laws of physics across the entire universe at the speed of light. Or maybe nothing happens. Maybe the universe just expands forever, becoming colder and emptier and darker, until even the concept of time becomes meaningless because nothing changes anymore. That's the ultimate void. Not just empty of matter, but empty of process, empty of change, empty of meaning. But we're not there yet. We're here, now, in a universe that's full of stars and planets and life. And that means something. It means we have the opportunity to experience, to learn, to create. The fact that it won't last forever doesn't make it less valuable. If anything, it makes it more valuable. We're living in the universe's golden age, its brief moment of maximum complexity and beauty, before the long decline into darkness. We should make the most of it. Let's talk about dark matter one more time, because it's one of the strangest aspects of the void. We know dark matter exists because we can see its gravitational effects, but we have no idea what it's made of. It's not made of atoms. It doesn't emit, absorb, or reflect light. It doesn't interact with the electromagnetic force at all. It passes through normal matter like a ghost, and yet it's everywhere. It forms halos around galaxies, providing the extra gravity that holds them together. It shaped the large-scale structure of the universe, providing the gravitational scaffolding around which normal matter collected to form galaxies and clusters. The leading candidates for dark matter are WIMPs, weakly interacting massive particles. These would be particles that interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Dozens of experiments around the world are searching for WIMPs, using ultrasensitive detectors buried deep underground to shield them from background radiation. So far, no one has definitively detected a WIMP. Other possibilities include axions, hypothetical particles that are much lighter than WIMPs but equally elusive. Or maybe dark matter is something else entirely, something we haven't thought of yet. What we do know is that dark matter shaped the universe. In the early universe, before atoms formed, normal matter, baryonic matter, was coupled to photons through electromagnetic interactions. This coupling created pressure that resisted gravitational collapse. But dark matter doesn't interact with photons. It could collapse under gravity without resistance, forming the first structures in the universe. Normal matter then fell into the gravitational wells created by dark matter, forming stars and galaxies. Without dark matter, the universe would be very different. Galaxies might not have formed at all, or they might have formed much later and been much smaller. Life might not have arisen. We owe our existence, in part, to this invisible, mysterious substance that fills the void. And that's one of the most profound lessons of modern cosmology. The visible universe is just the tip of the iceberg. Most of what exists is hidden from us, invisible, detectable only through its gravitational influence. Dark matter makes up 27% of the universe. Dark energy makes up 68%. Normal matter, everything we can see and touch, is less than 5%. We're living in a universe we barely understand, surrounded by mysteries, floating in a void that's far stranger and more complex than it appears. But that's exciting, not discouraging. It means there's so much more to learn, so many discoveries waiting to be made. Every generation of scientists thinks they've figured out most of how the universe works, and every generation is proven wrong by the next set of discoveries. 100 years ago, we thought the Milky Way was the entire universe. We didn't know about other galaxies, about the expansion of space, about dark matter or dark energy. 50 years ago, we didn't know about dark energy at all. 20 years ago, we hadn't detected gravitational waves or imaged a black hole or found thousands of exoplanets. Imagine what we'll discover in the next 100 years, or the next 1,000. The void still has secrets, and we're just beginning to uncover them. Now let me bring this journey to its conclusion. We've traveled through the cold emptiness of the universe, from the quantum foam at the Planck scale to the vast supervoids hundreds of millions of light years across. We've explored the nature of spacetime itself, the behavior of matter and energy in the void, the fate of stars and galaxies and the universe as a whole. We've confronted the ultimate questions. Why does the universe exist? Why is there something rather than nothing? What is our place in this vast, cold, expanding cosmos? And here's what I want you to take away from all this. The universe is cold and empty and vast, yes, but it's also full of wonder. It's governed by elegant laws that we can understand. It has a history that we can trace. It contains structures of breathtaking beauty and complexity. And somewhere in all that vastness, on one tiny planet orbiting one ordinary star, life arose. Consciousness emerged. We happened. Against all odds, in defiance of entropy and the march toward disorder, matter organized itself into forms complex enough to ask questions about the universe, to seek answers, to marvel at the strangeness and beauty of existence. You are part of that miracle. You are made of atoms forged in stars, organized by 4 billion years of evolution, animated by electrical and chemical signals that we're only beginning to understand. You carry within you the history of the universe, from the Big Bang to the present moment. You are, quite literally, the universe becoming aware of itself, experiencing itself, trying to understand itself. And that's not a small thing. That's everything. The void is vast, but you are here. The universe is cold, but you are warm. The darkness is deep, but you carry light. You are conscious, aware, alive in a universe that is mostly none of those things. That makes you precious. That makes your existence meaningful, not in some cosmic predetermined sense, but in the sense that you get to create meaning, to choose what matters, to decide how you'll use the brief time you have. And collectively, as a species, we're doing remarkable things. We're exploring the solar system, studying distant galaxies, mapping the cosmic web, detecting gravitational waves and neutrinos and cosmic rays. We're learning how the universe works, from the smallest quantum fluctuations to the largest cosmic structures. We're asking the big questions and finding answers, slowly but surely piecing together the story of how we got here and where we're going. We're also creating art, music, literature, philosophy. We're building civilizations, forming connections, loving each other, caring for each other. We're passing knowledge from generation to generation, standing on the shoulders of those who came before us, reaching higher, seeing farther. We're the universe's way of appreciating beauty, of creating meaning, of fighting back against the cold and the emptiness and the eventual heat death. And yes, we'll fail eventually. Entropy will win. The stars will die. The universe will cool and expand and become ever more empty and cold. In the ultimate end, trillions of years from now, everything we've built, everything we've learned, everything we've experienced will be gone, erased, forgotten. The void will reclaim everything. Heat death is inevitable, but that's not the end of the story, because the story is not about the ending. It's about the journey. It's about the brief, glorious moment when the universe is full of light and life and consciousness. It's about what we do with the time we have, how we choose to live, what we decide matters. The fact that it ends doesn't make it meaningless. If anything, it makes it more meaningful, more precious, more urgent. Think of a sunset. It's beautiful, but it doesn't last. Within minutes, it's over. The colors fade. The darkness comes. Does that make the sunset meaningless? Of course not. The fact that it's temporary, that it's fleeting, is part of what makes it beautiful. You appreciate it while it's happening because you know it won't last. Life is the same. The universe is the same. We're all temporary, all fleeting, but that doesn't diminish our value. If anything, it enhances it. So when you look up at the night sky and see the stars, remember, you're looking at light that has traveled across the void for years or decades or centuries to reach your eyes at this moment. You're connected to the cosmos in a very real, physical way. The atoms in your body came from stars. The energy that powers you came from the sun, which will keep shining for another 5 billion years. You're part of an unbroken chain of existence stretching back to the Big Bang and forward to the far future. And you're not alone. There are billions of other humans on this planet, each one a conscious being, each one grappling with the same questions about existence and meaning and purpose. We're all in this together, passengers on a tiny spaceship called Earth, hurtling through the void at hundreds of kilometers per second. We're all made of stardust, all children of the cosmos, all trying to figure out what it means to be alive in an indifferent universe. The universe doesn't care about us. It doesn't care whether we survive or perish, whether we thrive or suffer. The void is not malevolent, but neither is it benevolent. It simply is vast and cold and ancient, indifferent to our struggles and our triumphs. But we care. We care about each other, about our planet, about our future. We care about truth and beauty and justice and love. We care about understanding the universe, even though the universe doesn't care about us. And that caring, that capacity to find meaning in a meaningless cosmos, is what makes us human. It's what makes us special. So embrace the void. Don't fear it. Don't let its vastness make you feel small or insignificant. You're not insignificant. You're a part of the universe, as much a part of it as any star or galaxy or black hole. You're made of the same stuff, governed by the same laws, part of the same cosmic story. The difference is that you can appreciate that story, can understand it, can add your own chapter to it. That's your privilege and your responsibility. Live fully, love deeply, learn constantly, create abundantly, be kind, be curious, be brave, ask questions, seek answers, wonder about the universe and your place in it. And remember that for all its cold emptiness, for all its vast indifference, the universe has given you the gift of existence, the chance to experience and understand and appreciate. That's not nothing, that's everything. The cold emptiness of the universe is real, but so is the warmth of human connection. The void is vast, but so is the capacity of the human mind to comprehend it. The darkness is deep, but so is the light we can bring to it. We are small, yes, but we are mighty. We are brief, yes, but we are brilliant. We are the universe's most complex creation, its most remarkable achievement, its best answer to the question of what matter can become when it organizes itself just right. So when you feel lost in the vastness, when the cold emptiness of space makes you shiver, when you wonder whether any of this matters, remember, you are here, you are conscious, you are alive, you are reading these words, thinking these thoughts, feeling these feelings. You are part of the greatest story ever told, the story of the universe itself, from its fiery beginning to its cold end, and everything in between. You matter. Your life matters. Your choices matter. Not because some cosmic force says so, but because you decide it so. You create the meaning. You are the light in the darkness. The universe is cold and empty, but you are warm and full of life. The void is silent, but you have a voice. The cosmos is indifferent, but you care. And in the end, that's what makes the difference. That's what makes the universe worth existing in. Not its size or its age or its eventual fate, but the fact that within it, somehow there are beings like you who can look up at the stars and wonder, who can think and feel and love and create, who can ask questions and seek answers and find meaning in the meaningless. This is your moment. This is your time. The universe is 13.8 billion years old, and it will exist for trillions more. But right now, in this brief cosmic instant, you are here. Make it count. Live with intention. Love with passion. Learn with curiosity. Create with joy. And know that every moment you're alive, every breath you take, every thought you think, is an act of defiance against the cold emptiness of the universe. You are the rebellion. You are the light. You are the meaning in the void. And that, in the end, is the answer to the emptiness. Not that we fill it with matter, or that we conquer it with technology, or that we escape it by fleeing to the stars, though we might do all those things. The answer is that we fill it with meaning. We look at the vast, cold, empty universe, and we say, this matters. We matter. Life matters. Consciousness matters. The brief moment of warmth and light and complexity matters, even if it's temporary, even if it ends. It matters because we say it does, because we decide it does, because we are here, aware and alive, and we refuse to let the void have the last word. The universe began in fire. It will end in ice. But in between, there is us. There is life. There is consciousness. There is meaning. And for as long as we're here, for as long as any conscious being anywhere in the universe is here, the void is not truly empty. Contains us, contains life, contains hope, and that makes all the difference. Welcome to the cold emptiness of the universe. Welcome to your home. It's vast and ancient and strange, but it's yours. You're part of it and it's part of you. And together, for this brief cosmic moment, you and the universe are creating something beautiful. The experience of existence itself, the miracle of consciousness, the triumph of life over emptiness, warmth over cold, meaning over indifference. That's your legacy. That's your gift to the cosmos. That's why you matter. Now go. Live, love, learn, create, wonder, and remember, you are stardust contemplating stars. You are the universe looking back at itself. You are the light in the darkness, the warmth in the cold, the something in the nothing. You are alive in the void, and that's the most amazing thing of all.